Dear colleagues, Moscow time is 10 o'clock. We have a rather busy schedule today, and let me start our meeting. Its working language is English, so I ask Russian participants to understand. I already start to forget English. No, not much communication last years, but anyway, good practice here. And this is already 15th, it's a great number, Moscow Solar System Symposium. And I want to remember the roots of this symposium. I'm happy Professor Bazilevsky is present, is here. And we follow very successful, I think about 50 meetings, Braun-Vernadsky Symposium on space geology, which was performed by Vernadsky Institute at Brown University. But 15 years ago, we decided to merge our efforts and expanded the topic of this planetary meeting, and it now includes everything, and both space geology, we of course keep it as before, and atmospheres, also planetary atmospheres, exoplanets, many sessions devoted to different aspects of moon exploration. So we have a rather wide scope of the meeting. And also traditionally at this 15th meeting, we also split the days for first Mars. Mars is the red planet, it always was first priority in Soviet Union. But for Russia, I think the more important is Venus now, and we're working, Venus Day will be at Wednesday, and special attention will be given to the moon exploration, results of studies of lunar regolith. And I use this chance to congratulate our Chinese colleagues who are present here with great success of their Chinese Chang'e 5, Chang'e 6 missions, and we hope at the day after tomorrow, at Wednesday, we have special session devoted to comparative analysis of Chang'e 5 samples and Soviet Luna 16 samples. I think it will be already, results are preliminary, but already very interesting. Everybody is welcome to come. And last days we study also the exoplanet, as I said. And this meeting is different a bit from others because many attention will be given to giant planets. We traditionally not much attention was at previous meetings was devoted to Jupiter, Saturn, because not much activity in Russia and our close partners with this giant planet. But today we also have a look what's going there, and maybe we also have some plans, maybe international plans for exploration. I will not speak for a long, my speech will be short because we have many interesting talks today, and it's better to expand the time for talks. But I want to introduce one important event which will be here. Как включить презентацию? Как убрать эти? Okay. We decided to introduce new award. It's related with the name of Vasily Ivanovich Moroz. You see the dates of his life, famous planetary scientist, Russian and both Soviet, Russian and international, founder and former head of the Department of Planetary Physics. Oleg Korablev was his student and now follow him in this position. And he was pioneer of infrared astronomy. He devoted his life to research of solar system, planets, satellites, comets, minor bodies, and he was awarded by many state and international decorations, Order of Red Banner, USS State Premium, and I think maybe most important for his heart was a Kaspar Award for pioneering achievements in planetary science. You see the dates. He got it just at the year of his death, but was important for him that his activity was recognized. Moroz was the founder of infrared astronomy, as I said, and he started these experiments in 1959 with infrared spectrometer and ground-based telescopes in Crimea. And he achieved some interesting results for Mars and Venus, but for us, he was a teacher. I also studied his book as a student, and his monograph in '67, Physics of the Planet. Another book about planet Mars was at the shelf of all planetary scientists all over the world, and especially in Russia. And Vasily Moroz was active participant of planetary studies at all Soviet Mars mission, Mars 3, Mars 5, all Veneras 5 to 16. It was great achievements in this time, and he also participated and was key person in planetary science and cometary science for Vega, Venera, Galley dual space missions. And his last activity was international. He was he was PI of many experiments at Mars Express mission, and this mission was really successful. And we are very proud that Russia and European Space Agency successfully joined their efforts at that time in Mars exploration. And this will be Vasily Moroz Medal. It will be given for important contribution to planetary science, all scientists all over the world. And first ceremony for this medal will be at Thursday, четверг, at our conference dinner. Everybody is welcome, and among you are the awardees of this meeting, but I will not open the secret who they are. But it will be given annually each time at the symposium, Moscow Solar System Symposium 16, 17, and 75. I think we have enough medals for the end of the century. Okay, I think that is all what I want to say. One announcement which I want to give for today. After the session, we have icebreaker party as usual, and everybody is welcome to join it. It will be downstairs at our exhibition hall. And after this, in this room, will be very interesting movie about scientific studies of the lake of the lake in Antarctica. I forget exact title about it. It was international studies of some primitive life there, was very famous studies, and those participants of this investigation will comment this movie tonight. It will start at 7 o'clock. Thank you very much. If there are any questions to me on behalf as an organizer of this meeting, I am ready to answer. If not, we could continue. But before this, I have one very important privilege. As I mentioned, we have very interesting and close cooperation with our Chinese colleagues. And this is really going successfully. Everybody have heard about International Lunar Research Station, which we are actively working these days. And we have a bright future for this international cooperation. And Russian mission and Chinese missions, we try to coordinate their science. And behind all activities, behind all successful events is somebody, some person, and this person is present here, and I am very happy that Dr. Xiang Hui is present here. We want to give you this award for successful establishment of Russian-Chinese cooperation in space science, especially in lunar science. And this is here are two persons, the President of Russian Academy and director of Chinese Space Agency, who signed the cooperation agreement. Also, it was related with your help and your activity. Please.
Okay. Thank you. This is a very, very big surprise. Thank you very much. It's a very, very big surprise for me. And you know, cooperation is very important for humankind, especially in space science. Now, I remember 2 years ago, I just arrived in Moscow and attended the 13th Solar System Symposium here. I just first time to meet all the Russian scientists here. So it's very exciting because when we stand here, we have some good ideas to cooperate in the future. So we need to push the scientists to sit together and to find the common point and to push our cooperation. So I'm very glad that I can make some effort to push cooperation in the lunar sample because this is a very small beginning. But you know, in China, we have a thing that the star can make the planet shining. So I just hope in the future we have more and more cooperation program. Okay, thank you. And before I participate in this important meeting, I have just prepared a speech because there have some important signal delivered to the Russian colleagues. So I will just to finish my task. It's about it's address for this symposium. Dear scientists, ladies and gentlemen, it's a great pleasure to be invited to the Space Research Institute of the Russian Academy of Science to attend the 15th International Solar System Symposium. Every year, the International Solar System Symposium is a grand event in the field of international space science, providing an important platform for scientists to exchange the latest research results and discuss future research directions. Here, on behalf of the Chinese Embassy in Russia and the China National Space Administration, I would like to congratulate the successful convening of the conference. Since mankind entered the space age in 1957, major discoveries and breakthroughs in space science, including solar system research, have continued to emerge, completely changing mankind's understanding of the universe and nature. It has also opened up many new disciplines, new technologies, and new industries, such as solar terrestrial physics, geodesy, aerospace medicine, and space communications. It is recognized as a generator of wealth, driver of innovation, and source of new theories and new knowledge. It is a field in which scientific and technological powers are competing to develop and seek revolutionary breakthroughs. It plays an important strategic role in national development. China attaches great importance to lunar and deep space exploration, actively conducts space science research, and maintains an open attitude towards international cooperation. Recently, Chang'e 6 achieved the world's first sampling and return from the far side of the moon, bring back 1,935.3 grams of samples. In the future, Chang'e 7 will conduct environmental and resource surveys of lunar polar regions and will carry 6 payloads from 7 countries and international organizations, including Russia, Egypt, Bahrain, and Italy. Chang'e 8 will conduct technical verification of in-situ utilization of lunar resources. Tianwen 2 will achieve the campaign flight and sampling return of near-Earth asteroid. Tianwen 3 will achieve the sampling and return of Mars and Tianwen-4 will realize the orbital exploration of Jupiter and its satellite. From Chinese first astronomy satellite, the dark matter satellite Wukong, to the quantum science experimental satellite Mozi, the comprehensive solar exploration satellite Kuafu-1, and the large field X-ray astronomical satellite Einstein probe. China has completed 15 space science satellite missions and created its own series of space science satellites. The SMILE mission, the Solar Wind Magnetosphere Ionosphere Link Explorer, is a China-Europe joint program in order to deepen the understanding of the Sun-Earth connection by observing the dynamic interaction between the solar wind and the Earth's magnetosphere. Now the SMILE satellite has completed the development work in China and is expected to be launched before the end of 2025. China's space station has been fully built and entered the application and development stage. It has carried out a large number of space science and application experimentals with a large number of scientific research results. 7 days ago, on October 15, 2024, China unveiled a national mid- and long-term development program for space science, which will guide the country's planning of space science missions and space research from 2024 to 2050. The program, the first of its kind at the national level, was jointly released by the Chinese Academy of Science, the China National Space Administration, and the China Manned Space Agency. The program outlines the development goals of China's space science, including 17 priority areas and 5 key scientific themes, as well as a 3-phases roadmap. So this is a good program to be started by you, because you can find some of the cooperation opportunity in the future. China is willing to work hand in hand with all countries in the world to continue to promote the exploration and peaceful use of outer space, and is ready to work with its international counterparts, including Russia, to strengthen exchanges and cooperation, to discuss the construction of International Lunar Research Station, to share the scientific and technological achievement of lunar exploration, and to jointly push forward the in-depth development of solar system scientific research, so as to contribute its wisdom and strength to the cause of space science for the humankind. Finally, I wish the symposium complete success. Thank you very much.
Very good moment. And I also want to give a floor to one of our colleagues who his career symbolized the international cooperation. This is Professor Dmitry Titov. He was also a student of Vasily Moroz, but I also was involved in his education because he was my deputy in the Council of Young Scientists of WIKI for many years, which was very active at this time. Then Dima moved to Germany in the 90s when not much activity, science activity was in Russia. Then he moved to ESTEC and was project scientist of Venus Express. And now Dmitry works in China in Canton. Yes, but he will explain himself. So it is very international and interesting career, and he maybe welcome us and say something about it.
Well, thank you very much, Lev, and good morning, everyone. So it's really a pleasure. It's really unexpected because Lev just asked me to talk about this. Well, while at European Space Agency, I was really the project scientist for Mars Express, for Venus Express, and then study scientist for JUICE and Envision missions. So, and after retirement from, before retirement, I was the contact person for the Tianwen-1 between Tianwen-1 team and Mars Express team, or Chinese scientists and European scientists. It was a pleasure, and I think it was really very good collaboration, because really Mars Express flying and mature mission was really providing data to the Chinese in preparation of the landing of Zhurong rover. So I think it was very nice, and now it worked, and really I applaud to Chinese scientists and engineers how successfully they managed to do these things. And I hope this collaboration will be continuing, and especially a pleasure for me, since I went from these walls. I made my PhD here, worked with colleagues here, so it's really a pleasure to see you, Chinese colleagues, and now I'm working in the Sun Yat-sen University in Zhuhai, and really trying to establish collaboration, doing what I can in this position. So thank you very much, and I hope we will have a fruitful meeting and discuss and look into the future. Thank you so much.
If no any other speakers for opening ceremony from our guests from other cities, other countries, okay. If no, let's start our regular session, and I want to give the floor to Oleg Koroblev, who is will chair it, and I wish everybody successful day today and successful 4 days afterwards. A lot of new interesting results and discussions.
Good morning, dear colleagues. I am happy to chair this first part of our session. We still have some time. Lev Matveyevich did not use his allocation fully. But I hope we can maybe start a little earlier. We were supposed to start in 15 minutes, but maybe I will first talk a little bit myself. I will introduce the first speaker. Anna Fedorova will reveal our achievements on one very important mission in which many of us were involved. Mars Express has celebrated 20 years in orbit early this year. It was launched in 2003, reached Mars in 2003 December. There was a Beagle 2 probe on board, which as we know later landed successfully, but never worked. It was partially deployed, and all we know about that it sits safely on the Martian ground, but it never communicated to any orbiter or to the Earth, and probably never conducted any measurements. But the orbiter, I would say the main part of the mission, which was devoted to recover a great share of science which was planned on previous mission, Soviet and Russian mission, which it was in between, in transition. Mars 96, it was first Mars 92, then 94, 96 it was launched. But it was not successful, but many instruments were with European participation, and even European instruments. And at that time it was a difficult transitional period for Russia. Nobody could dare to restart such an ambitious effort, but Europe succeeded to push forward a very modest satellite with several scientific instruments, 7 if I remember well, and well, it works since then. It's in orbit, delivers great science, and Dmitry Titov, to whom you have listened just, was some period of his career. He was a project scientist of Mars Express. So this year, well, actually it was maybe last year, there was a major effort undertaken by Dima in particular, a series of space science review papers dedicated to Mars Express results. Now they are starting to come out, and our speaker Anna is co-authored 4 or 5, I don't know, many of them dedicated to Martian atmosphere. So she is entitled to give such a review. Maybe I could already give her some floor. Maybe you can spend a little bit more time, but not too much, please.
Okay, thank you very much. So I can start?
You can, yes, you can start, please.
Okay, so I will present some survey of the Mars Express observation, mainly of course concerning to my study and study of my colleagues in Russia. So now we know about Mars, not everything, but plenty of knowledge. We know that Martian atmosphere is cold and dry. We know the composition of Martian atmosphere. It is mainly composed of CO2 molecule. We know the pressure on the surface. We know the climate of Mars. We have the mapping of water vapor, the aerosol, the dust, the clouds on Mars. We know the distribution of temperature. We know the main seasonal cycle on Mars, like the water vapor, dust, and the CO2. We know about the evolution of Martian surface. But this knowledge was impossible without intensive study of Mars with spacecraft. Thank you, Oleg, for some introduction, but I also made it in my presentation. This is this slide present some survey of the mission to Mars, beginning from early mission, where was a big participation of Soviet Union with the Mars spacecraft and landers, not very successful, but some of them take a new result, especially about the upper atmosphere. And since the 19 years, the extensive study of Mars begin with Mars Pathfinder rover and Mars Global Surveyor orbiter. So here you see the images of orbiters that operated on Mars orbit or still operated. And between this, it was a little shifted of the lines, but between this orbiter, the Mars Express mission that was launched in 2003 is still operated and now have a 20 years celebration. So it's one of the oldest mission still working on Mars orbit. Again, some history. In fact, Mars Express is a child of Russian Mars 96 mission. In 16 November 1906, Mars 96 mission faltered during the launch, and it was the most complex mission that ever was sent to the Mars. And it was very strong international cooperation, including the colleagues from Europe mainly, from France, Germany, and Italy. So after these tragical events, especially for the Soviet team, for the already Russian team in that time, the European community very fast organized the Mars Express mission, first European expedition, with this length that cheaper, better, and faster. So this vision was dedicated to the study of the atmosphere and surface and history of climate of Mars. Several instruments from the Mars 1906 mission, like the HRC camera, Omega imaging spectrometer, Fourier spectrometer PFS, Aspera, and SPICA, was heritage from Mars 96 mission. It was extremely strong international cooperation, and for us, it was continuous participation in a few instruments on both Mars Express mission. Of course, it was not so strong like the Mars 96 spacecraft, that was the Russian experiments, but we still have the teams of scientists that participate and contribute to the several instruments on Mars Express. Particularly the contribution where we Russia was able to provide some important elements was Omega, PFS, and SPICA. Mars Express was launched in 2nd June 2003 from Baikal with Soyuz Regat, and it was inserted in Mars orbit on 25 December 2003. And the science program of the spacecraft began in January 2004. So in the beginning, Mars Express have 7 scientific experiments on board. This is the high-resolution stereo camera, the MARSIS, radar for subsurface and atmospheric study, the Mars radio science experiment, the Aspera, analysis for space plasma, and the 3 experiments that provided some elements for instruments that would come from our department in IKI. It's Omega spectrometer, with and PFS Fourier spectrometer with deep participation of Vasily Ivanovich Moroz laboratory, and SPICA ultraviolet and infrared spectrometer, very small experiments for study of the Martian atmosphere. So it's impossible to talk about everything. I will speak about the experiment that is close to me and close to my colleague in the our planetary department. Interesting experience of Mars Express that since 2016 the visual monitoring camera that previously was considered like the technical instrument on Mars Express was also involved in science study, the imaging of Mars, the atmospheric process of Mars. So now on Mars Express we have 8 scientific instruments, including the VMC camera. And if I remember right, it's also we have 9 technical experiments that also is involved, but I don't include it in this slide. So Mars Express has high elliptical orbits with periapsis about 300 kilometers and apopsis about the 10,000 kilometers. It's allowed to study the atmosphere and surface, including geology, mineralogy, the seasonal effects, climate of the Martian surface process, the polar caps, the subsurface structure, the atmospheric composition, the atmospheric vertical structure, density, dynamical effect, thermal structure, clouds and dust, water cycle. And also, of course, the study of the satellites of Mars, Phobos and Deimos, during the close transition with them. The Mars Express orbit allow the different observation, not only nadir and limb, but also the solar and sun occultation that quite important for vertical structure of the atmosphere. So the Mars Express was the second mission of Mars after the Soviet Forest 2 that applied with this methodology to the study of the atmosphere of Mars. So I begin the main result, and I will concern mainly results where the Russian co-authors was included. So the Omega. From the Omega, the imaging mapping spectrometer based on the gratings from the visible to the middle infrared range. Strong Russian collaboration because the scanner system was provided by IKI and Corex. Here the old photo, including the colleague from our department, Vladimir Katsov, that present the scanning system for Omega instrument. So because it's imaging spectrometer, it's it have low spectral resolution. It's very good for study the mineralogy on Mars. So here you can see the example of the track of the spectrometers providing the different signature on the surface of Mars. The two main findings that was involved concerning the first polar cap. It was the discovery of the water ice on the south polar cap of Mars. Previously, it was known before Mars Express that the south polar cap the basic polar cap, soft polar cap of Mars consists of CO2 ice. It was seen from the high albedo and low temperature of this polar cap. But with spectroscopic instrument, Omega, it was shown that it's not only CO2 ice, but the water ice was closed in this polar cap, and the CO2 ice are mostly presented above this CO2 ice. So it makes study the long-term evolution of a polar cap that's related to precision, the change of the precision of the precession of the Martian axis, and that during about the 2000 Martian year, the water transfer from the one hemisphere of Mars to the other and collected and moved from the one pole to the other poles. The another finding of Omega in the beginning of the mission and the global mineralogical mapping of Mars, thanks to the observation of hydrated minerals and the main rocks on the surface. And this study that was published by Jean-Pierre Bibrink in 2006 mainly construct the geological history of Mars that show that in the beginning Mars was the wet planets, but in the first billion years with some very extensive process that happened on Mars, like the volcanism was stopped and over and changed Mars evolution to the cold and dry to cold and dry Mars. So the another spectrometer, the so small become spectrometers in the UV range from 100 to 300 nanometers and infrared from 1 to 17 nanometers. The infrared spectrometer based on acousto-optical tunable filter methods. It was very small, very compact, and mainly dedicated to atmospheric study. And because this spectrometer work in solar and stellar occultation, it was one of the instrument on Mars Express that allow to study the vertical distribution of the mineral species in the atmosphere. The main mineral species that was dedicated of SPICAM, it's ozone on Mars and the water vapor on Mars. What it's allowed to do, this is the it's a long-term monitoring and multi-year climatology on the Martian atmosphere that was obtained of this SPICAM for several years. This is the multi-year monitoring of water, ozone, emission, dust, and water ice. First purpose of this SPICAM was to study simultaneously water and the ozone to understand the photochemistry of the Martian atmosphere. And here you see the simultaneous observation of ozone and water that show the anti-correlation, because the water, in fact, in the main molecule that destroyed the ozone, not only on Mars, but also in the Earth atmosphere. And also the ozone layer on Mars was firstly observed by the SPICAM of the spectrometer. So SPICAM was the first before the MAVEN mission that allowed to construct the ozone cycle on Mars and make some understanding what government the ozone cycle. For example, it was found the important role of water ice clouds that absorbed the hydrogen radical on Mars, and that could explain the observed anti-correlation of water and ozone and discrepancy between the model prediction of general circulation model prediction of photochemistry from the SPICAM observation. The oxygen emission was also observed by Mars Express. SPICAM and OMEGA observed the 1.27 emission. On the day side, it is a tracer of ozone, and our colleague contribute in the multi-year observation of this emission as a tracer of ozone. We've also studied the anti-correlation of the emission and the water vapor. And the OMEGA, thanks to the high spatial resolution, firstly allowed to observe this emission of Mars the gravity waves that was published about already 15 years ago, but the contribution of Russian colleagues by our Italian colleagues, Francesca Altieri. The discovery of Mars Express was also air glow, like the oxygen of the night side and NO also on the night side. NO from UV, it was a pioneer work in science by Berthaud et al. 2005. And in 2012, OMEGA discovery on the night foil the oxygen emission that then was continued by SPICAM also on the north and south pole. And this emission is a very good tracer of the dynamics on Mars. It's still used already in our mission to study the dynamical fluxes on Mars. The another discovery in Auroras, we participate in the beginning, not in the late mission. So the Cameron bands of CO and CO2 plus was published by Berthaud 2005. And this Aurora, it's related to residual magnetic field of Mars in the southern hemisphere. Here you can see distribution on emission correlated with this main magnetic field. The H2O monitoring, the topic was mainly related to me. All three instruments made it, so we made firstly the total global monitoring of water after the first mission like Viking and TEST, and in all spectral range practically what water can be measured. So we made the conclusion about the interannual variability and how to dust influence to the water on Mars. And of course water, it's an important topic because where's the water, if we have the wet Mars, where's the water on Mars now, how Mars lost the water. And SPICAM, thanks to the vertical profiling of water vapor, helped to partially, at least partially answer to this question. It was at least two discoveries by SPICAM from Mars Express mission. First, that the water can be strong supersaturated on Mars, which make the escape of water to high altitude. It's very very easy escape to high altitude. And second, that during the Mars global storm, dust global storm in Martian year 28, it's 2007, it was observed very high water, water that reached the 100 kilometer. From this altitude, water can photodissociate and be directly source of the hydrogen, the atomic hydrogen on Mars. And it can increase the escape rate of hydrogen from the our atmosphere at least in 1 order of magnitude. This is the simultaneous observation made from SPECAM OF of the Lyman alpha emission that indicated the hydrogen escape of Mars, and this is the observation of the amount of water during this year, the black points that show that water can reach very high altitude. In fact, this observation it's totally changed the paradigm of water escape from the atmosphere. It's happened only 10 years ago, helped to Mars Express observation. Also, Mars Express firstly showed the seasonal cycle of vertical distribution of Mars, and it was clear that the perihelion season that Mars very close during the soft summer, it's also can rise water very high in the atmosphere. So the equation of the impotent role of the global dust storm and the perihelion season of the escape of Mars is now discussing and in calculation. Aerosol. Mars Express become also my vertical profile of aerosol with several findings. First was detected the bimodal distribution of the aerosol of Mars by Mars Express. The haze variation with altitude, and first subvision observation of CO2 ice clouds with this SPECAM UV spectrometer of Mars. I was the child of Vasily Ivanovich Moroz, the planetary Fourier spectrometers. You know, the important experiment where I participate, at least for the first part of the mission, it was involved very much. It's a huge instrument dedicated to the climate study of Mars. Here you can see already published without our Russian colleagues and participate in the beginning, the study of the temperature evolution, the dust opacity and the ice opacity, like the for example, TESS experiment of Mars global surveyor, but it was the United States result, but here it's a result of spectrometer that was practically designed in Space Research Institute. Minor gases, I would say the most exciting finding that stimulated not only the study but the spacecraft development, like the Trace Gas Orbiter mission. It's first publication about the methane detection was made with Fermizana with participation of our colleagues. It was plenty of questions how the PFS was sensitive to the methane, but I don't think it's too important now because it's stimulated so work a study of the possible methane distribution of Mars and the source of methane, its lifetime. And here you can see already the recent observation of PFS with the Italian team, and already our observation of ACS that not confirm its presence of Mars, but in fact it's a long story that can be dedicated to this separate big topic. Also, we participate of CO study, at least in the beginning, the important gas and uncondensable gas with very well tracer of the condensation of the Martian atmosphere, because the CO2 atmosphere of Mars is condensable, and to observe it, it's possible to use incondensable species, and CO it's a good example, and this is the map of the PFS observation along the all experiments around on the Mars orbit. But the contribution of PFS here, it's quite important. Returning to the surface, I said that we participate in the surface, Russian participates in the surface study with these experiments in the beginning of the mission. But of course, our colleague continue. Here you can see the evolution of polar cap of Mars made by Omega spectrometers. But our spectrometers become it observed 20 years already. It also can study the ices and the Martian atmosphere. It was not considered as a surface spectrometer from the beginning because it was dedicated to the atmosphere. But looking on high resolution ices spectra, after the 20 years of observation, it looks that the new finding is still possible. So it's possible with high resolution spectra of infrared spectra of ices can contain information about isotopologues on Mars that equate to the evolution of polar cap of Mars, and it works of our young colleagues Alexander Lomakin that is now in preparation for publication. So what we have for 20 years, many instruments are not working now. Only with this channel of omega, if I'm right, on this infrared channel, I know very well it's become on Mars Express. Laser diode anomaly by PFS don't allow to make some observation and sites now. It's only small amount of data. Many anomalies with over experiments of Mars, but in this year, this mission has a prolongation at least 2026, and in this year we have a special issue on Space Science Review on summarizing 20 years of Mars Express observation, part of which I just told, and where is about I don't remember 12 or 15 papers. If Dmitry Titov would know, it's like about 20, like the editor of this special issue. But in this special issue, our contribution of our department is quite prominent. So we're happy with this result of Mars Express. Thank you very much.
Thank you, Anna. We have time for questions. Please,
One or two questions. First question. This year, you know, Gerard and others published in Nature Astronomy results of about a visible region, namely second Hertzberg system in the atmosphere of Mars in night glow. This spectrum is similar to measurements by Krasnopolsky on Venera 9 and Venera 10. Why we so long time waiting for these results? On Mars Express, the spectrometer invisible region was absent.
It's need to. No, it's not absent. In fact, it's a mega experiment that has a visible range. But I don't know too much results from a mega visible channel. It was some problem with calibration from the beginning, if I remember right. So this result for the oxygen, it's coming from the NAMAD experiment. Yes, right? From the NAMAD to this channel. I think the science project manager of the of the Mars Express could say more about the omega visible channel and why it was a problem to observe this emission on the night side. In fact, potentially it could do it. Maybe it's not very sensitive. It was not very sensitive problem of calibration. We are not involved in this channel of omega.
Yeah.
Yes, right. Yes. Mars Express has observation for photon free emission. At least from PFS, I don't know about Omega in the beginning of emission, but I was not involved in this study. So, but in Air Glow survey in this special SU, it was a part dedicated to this emission 4.3.
General question. What organic molecules detected on Mars besides methane?
It was formaldehyde, for example, but it's a questionable. It was a Phobos 2 mission. It was published at '93, but it was not. Still, it was not confirmed.
Well, methane is the simplest, but it is still debated. So
Yes.
more complicated molecules are even more debatable, I would say. Any more question for Anna? Yes, please, let's thank her again. Very nice review. By the way, it's an interesting question. Why did Omega could not observe this green line, which is so bright and very small NOMAD UV instrument in NOMAD? It's really a tiny thing. It sees this easily, I would say, no, more or less.
Well, I don't know, frankly, but the situation is that, well, the teams are focusing on something, so there's not a big team in Omega. So that's why, as a project scientist, that's what I see every day. And probably simply those people were mainly interested
In the surface, in the surface.
So that
Yeah.
there are a lot of data in the HRC camera, the camera in Omega related to the atmosphere, which are not analyzed. So basically their data are in the archive, and no one is working on them.
Yeah,
So that's
so-
oh, I'm sorry.
So
Yes,
there-
so that's why I think I'm in every conference I'm really calling to the people, go to archive, take the data and work on them.
Thank you. We are right on time. The next speaker is Alexander Lomakin. He will dig a little bit deeper into surface data of SPICAM, introduced by Anna. A nice piece of Mars Express. More or less fresh Mars Express science.
Okay, hello everyone. So today I will be talking about aerosol scattering correction of SPICAM-AR surface spectra. It will be more of a methodology talk than results, but I still believe it might be quite interesting to talk about this. Just to recap SPICAM-AR characteristics, the spectral range is from 1 to 1.7 microns. The resolving power is around 2000. As Anna mentioned before, SPICAM wasn't really designed as a surface spectrometer, but in the spectral range, there are bands of CO2 ice here, for example, these ones here, sharp ones, and a broad absorption band of water ice. So the observation scheme is the following. We observe the reflected solar radiance in the air from the polar caps, which passes through atmosphere and goes straight to the detector after reflecting. Usually the geometry is nadir, but sometimes we can have some emission angles here. The first step, which was done before, it is not new results here. It was the gaseous correction was done because in order to have some surface spectra, we have to first of all clear the influence of the atmosphere, and these are absorption bands of the atmosphere of CO2 and water vapor. So the this is how the retrieved spectra from the South Pole look like. So you can see that there is a quite some diversity of spectra. These sharp features here and this big feature, these sharp features, this big feature, these sharp features are the CO2 ice, and the broad band here on the red spectrum is water ice feature, 1.5 micron feature. As you can see, CO2 ice can be quite different on the surface, and the spectrum can look quite different. This is still CO2 ice, but some of the bands are much broader. That's because its physical characteristics are a little bit different. We retrieved these surface spectra, but we wanted to map these features since we have a huge data set, which consists of more than 1.5 million spectra of like around 100,000 of them at least have some CO2 ice in them. In order to somehow map the CO2 ice, we had to quantify the band depth here. We use interesting metric here, the equivalent width of the band, which comes from the astronomy. Here, you can see the formula here. It's basically the like inverted integral, so the normed integral of the band here. And for water ice, we use the just standard depth of the band index, which was also used previously in omega. So this is how the seasonal maps look like. So as you can see, we have these are seasonal maps with all of the years averaged here. We have the recession of South Polar Cap, which is very nicely mapped, and as you can see, there are some variations here of CO2 band depth here, and also for water ice, you also can see the recession of North Cap and some water ice on the South Cap here. But in order to have better results and more precise results, we actually have to not only consider the gaseous absorption in the atmosphere, but we also have to consider scattering on the aerosols and on the dust in the atmosphere. As you can see on the scheme, some of the solar photons scatter on the particles in the atmosphere, and actually there might be some multiple scatterings here, which we have to account for in order to retrieve true surface albedo. It has actually been done before, and you can see an example here from the paper of Langevin et al. 2007, which was dedicated to omega surface CO2 ice results and water ice results also. As you can see, the black and red are spectra without aerosol correction, and blue and green are corrected for scattering. And as you can see, one can expect the effect of some enhancement of like a contrast when we look at the ices. The deeper parts are deeper, the high albedo parts are even higher here. But how does one achieve these results? In order to stimulate this, in order to also try to retrieve the true albedo, you have to solve the radiative transfer question, at least partially, at least numerically. And the problem here lies into this integral, which is in which scattering is involved, and to deal with multiple scattering, the best way is to use end-stream algorithms. These are the most used ones, and they are tested on various other missions and instruments before. For example, this sort, which we used, as you can see, the sample from the ADS abstract search is very highly cited. It is used in a lot of papers. It's a very known algorithm because it is quite complex and precise. As we use dSort as inputs for dSort. For optical parameters, we used dust optical parameters, which is widely used in literature and just generally in the pipelines. That's Wolf parameters. And for dust climatology, we used MCD 6.1. And essentially, the Montabone dust modeling is incorporated in the MCD here. So it is a very complex and very a good source on the information about dust. We could actually use PFS dust climatology, which would be collocated with SPICAM, but for us it is for now it is simpler to use MCD, but we consider to use PFS in future. Since we now have the forward model and we are able to use it, let's talk about how the dust scattering influences the albedo. Let's have an example here. This is what people usually think about when we talk about the CO2 ice in the surface. So a bright ice with a very big CO2 ice band here. Let's try to add some dust. For example, if we inject a little bit dust in atmosphere, for example, optical depth 0.5 here. If we insert it, you can see that there is some, the albedo here goes lower, but here albedo actually doesn't change too much. And if we insert more and more dust, you can see how the albedo of the surface, the apparent albedo, changes here. That's what we observe with the spectrometer here. And as you can see here, the continuum albedo here, it actually decreases here. That is because the albedo of dust here is just generally much lower than the albedo of pure CO2 ice here. But the important part here is that albedo in this part doesn't actually change. And if we remember how we defined the indexes and how just people usually define the indexes for CO2 ice and for mineralogy, they are usually normed by the continuum albedo here. And the consequence of that is that this difference in albedo and this way of this configuration of dust and CO2 ice on the surface doesn't actually result in a big difference in the CO2 ice. For example, at some point we had the equivalent width of this band as 70.5, and even with a huge amount of dust, we still have the 16 as CO2 ice index, CO2 ice equivalent band depth of the main band here. So it's not much different. But we will see completely another case in the different case here. So this is the winter, and just more or less typical for Martian South Pole case, when we have the transparent CO2 ice slab where we can see the surface. As you can see, the reflectance here is very dark. It's 0.25. So we can actually see the surface through the ice here. And as a result, we have a completely different thing when we insert the dust in the atmosphere. As you can see here, since the dust albedo is actually around, it depends from geometry, but it's 0.3, 0.4, and it actually, so the result is much different. And as you can see here, the band depth here changes hugely, and that results in the huge reduction of CO2 ice index, which is 10, and at a starting point it was 37 here. So how fast is the sort? How fast is to compute these observations? It's actually very slow, and we actually require to do some optimizations in order to really retrieve the spectral albedo of the surface. First of all, the first optimization that we can introduce here is to to use some approximations here, we still will call dsort to calculate the albedo of surface 0, albedo of with dsort with albedo of surface 0 and albedo of surface 1, but it will actually give us a great estimate of the true surface albedo of the Mars in that case. If someone interested, I can later show the derivation of the formula. And the second optimization that we can introduce is to try to calculate these not outside of the gaseous bands, because if you try to do this with including the gaseous bands here, you have to compute on the very fine grid, because you then have to convolve it with the ILS. This results in the following algorithm. First, we have the observations. We select the windows outside the gaseous bands. Then we input them into dsort, and then we extrapolate the initial spectra on these observations. And if we compare it with the just full retrieval, it actually is quite precise here. How much different are aerosol corrected indexes with this procedure here? It's actually not a big difference. As you can see, figure 1 here and figure 2 here are the comparison here. So figure 1 are pre-correction, and figure 2, the middle panel here, is post-correction, and it's not actually much of a difference here. And the biggest difference actually comes, this is the ratio of the new index to old index. And the main difference actually comes when on the edge of the cup, when the albedo is small, because the smaller the albedo and the higher the CO2 band, the more you have the influence of dust on the spectrum. And as you can see, there's just two-axis diagram, and one might expect that the dust optical depth is the main driver of the difference in indexes here, as we map them, of the band depth here, but this is actually the albedo, and if the albedo is high, essentially we do not care all that much about the dust optical depths. It will not influence the depths of the CO2 band too much. So the summary here, the multiple scattering model dsort was applied to Spicama-Yar spectra. We developed a fast algorithm to correct surface spectra from aerosols. The algorithm was further optimized with a small accuracy compromise, but huge speed increase and influence of dust on subset of Spicama-Yar ice indexes was assessed, and essentially high continuum albedo found to significantly reduce the influence of dust on spectral reflectance. And for plans for future, finalize the retrieval algorithm for surface albedo, assess the accuracy, add 3 parameters, and try algorithm on omega data. That's it.
Thank you, Sasha. One short question, if any. Actually, you have used your time up to the end.
Sorry.
I have questions, but I will ask them later. Yeah.
Okay.
Need to dig a little bit into the. Huh? No, nobody. Okay. Now we move from Mars Express to another mission active on Mars. ExoMars TGO. Mikhail Luginin will tell us about hydrogen chloride and some features of it. Actually, he is going to deliver 2 talks. His one and the following one. So please let some time for discussion. It's nice to discuss.
Thank you. Good morning. So my talk is about the interactions between the HCl in the atmosphere of Mars and the water ice. Okay. So first, few words about the history of HCl. Actually, the first detections were done in 2021. Before, it was only upper limits of the HCl. First, ACS detected the HCl. The observations were done in 2018. It was the year with the global dust storm on Mars. You can see that it started at solar longitude about 185. So actually, during the decline of the global dust storm, we saw HCl a lot of in the southern hemisphere. You can see the profiles. So some of the HCl was also in the northern hemisphere, but the much lower amounts. The HCl abundance was up to 4 ppb. So the fact that we saw HCl after the global dust storm, where a lot of dust was injected in the atmosphere, tells us that there is a connection between dust and HCl. Also, right from the first paper, we saw a striking similarity in the profiles between HCl and HO2, which was not obvious. And the ACS detection was confirmed by the NOMAD also on the trace gas orbiter. And actually, immediately after that, we studied the dusty season on Mars in the next year, Martian year. And we saw again that even without the global dust storm, just during the dusty season in the southern hemisphere, we see HCl, which actually quite rapidly vanishes. So this is like the first puzzle, because before with just photochemical sink, the lifetime of HCl was believed to be like 90 days. And we saw a rapid destruction of HCl. Again, we saw similarities in the H2O and HCl profiles. You can see the H2O and HCl are very similar. Even when we plot it in correlation figures, we see that, these are scaled number density, but they are on the straight line very good. Again, next we looked at the isotope topolog of HCl, and here we saw that actually the picture is like on Mars, or I'm sorry, on Earth. So actually, there is almost no increase in the heavy chlorine elements. And this is consistent with the known Martian soil properties. So this is like in favor of the hypothesis that HCl comes from the interactions with dust. Also, in 2020, there were a special campaign of observations from the ground-based telescope from the Hawaii Islands. There are two measurements in September and November of 2020. On Mars, it was again dusty season, on Martian year 35. In ACS, we were measuring in solar occultation, so we looked only on the one point on the planet. But here we could construct a global map of HCl, and we saw that actually HCl is not only in the southern hemisphere, but also we saw it near the equator. And actually, we saw that the HCl is at different parts of the planet simultaneously. And again, we saw similarities in the HCl and H2O abundances. So these were the observations, but too bad that we don't really know the sinks or the sources of the HCl on Mars. So we can see how is it on Earth. So the main source of HCl on Earth is sea salt aerosols, but also some coal and oil burnings, some volcanic releases. In stratosphere, HCl takes part in the ozone layer chemistry and in the seasonal polar ozone depletion. Also, HCl, there is an uptake of HCl onto mineral dust on Earth, and also on the waterized aerosols. This comes also from the laboratory measurements. And these laboratory measurements helped us to model some of the distribution and the seasonal figure of the HCl on Mars. And now we come to our observations. They are made based on the MIR, that is a middle infrared channel of ACS, and near infrared channel of ACS. From these instruments, we can simultaneously retrieve profiles of HCl, temperature, pressure, water vapor, and aerosols. So HCl retrievals are done in the same way as in the work from Trkhomsky 2021. We use an iterative Levenberg-Marquardt algorithm to retrieve all mixing ratios of HCl. And for retrievals of aerosols, we use both MIR and NIR channel. MIR contains waterized absorption band at 3 micrometer, actually part of 1/2 this band. And we use NIR that contains aerosol continuum. And we retrieve, we retrieve HCl, we retrieve temperature, water vapor, and mass loading of dust and water ice. We have analyzed 2.5 years of Mars from the second part of Martian year 35 and full years of 35 and 36. You can see on the right figures the southern hemisphere. Well, we see during the dusty season HCl is there, and to the values up to 5 ppbs, and some also HCl in the northern hemisphere during the dusty season. But actually, from these kind of figures, we do not cannot rule out is there some interactions between the dust and water ice. So we looked at the separate profiles. Here you can see an example. So the aerosol extinction, red and yellow are the those contribute to the water ice. It comes from MIR. So we can see that here from the 40 to 50 kilometers there's a gap in the water ice. And actually there is dust inside this gap. And inside this gap we also see a maximum of HCl and also of H2O. And from all this data set, more than 700 profiles, we saw 11 clear cases when we have HCl inside these water ice gaps, which we called ice holes. These altitudes actually of HCl maxima are clustered around 30 and 45 kilometers. So, and all the profiles allow us to construct some local anti-correlation figure between the HCl and the water ice content. Well, which tell us that there is actually uptake of HCl on water ice particles on Mars. And this fact allows us to make corrections to the estimated lifetime of HCl. With such mechanism, the depletion of HCl can be on the scale of 1 day, compared to 90 days with just photochemistry. And well, that's all.
Thank you, Misha. Right in time. The question is, Андрей Серафимович, снова садитесь поближе.
Thank you very much for the nice presentations. Nevertheless, it is known that in the atmosphere of Earth there is a influence of halogen components on ozone content, namely chlor, brom, phtor components influence on the ozone. Is this influence of halogen components in Mars atmosphere on ozone content in Mars atmosphere, or the concentrations are very small and we can neglect by this dynamics of content, namely halogen components in Mars
Thank you.
atmosphere?
Well, actually, the HCl content is like very low and sporadic. The ozone content is much lower on Mars, so actually we don't know.
I have an answer, but well, there was one study published also this year, the Benjamin Taisum and et al. In Astronomy and Astrophysics. They did some testing about ozone in particular. They did testing about methane, and the methane destruction is affected. But to show what's going on with other active components, they tested also ozone, and apparently it is not very much affected. But it's a very good question anyway. Mikhail, so
Okay.
if there are no question, so you could introduce a talk by Alexander Treskhimovsky. You have already did a nice introduction to that. Alexander is away at this moment.
Okay, so this is well a topic that covers some unexpected measurements of HCl, because well, I was talking about the mainly perihelion season or dusty season on Mars, and here we see the actually in the aphelion season we also have detections of HCl. Okay, so well, some of few slides I will skip. So here we also use ACS data, mirror channel, near channel. Well, before the ACS, only upper limits of HCl was known on Mars. On Earth, we have HCl on Earth that comes from the perchlorates and chlorates, but well, here, and also some of the HCl comes from the volcanoes on Mars, and well, volcanoes will take part here. So HCl, we can see HCl from different orders, from different lines, but well, actually Sasha is using only the middle one because they are isolated lines. Well, about the history, I will skip this completely. So there were, in Martian year 35, there were 2 detections of HCl in the aphelion season. You see two stars here. And these 2 detections led us to make a special campaign in the following observations in Martian year 37. So there was a special campaign that was targeting this period, and actually we succeeded. So in Martian year 37 we saw quite a number of HCl detections in the northern hemisphere that are actually quite localized. You can see here all the 3 years are pointed together, and in the aphelion season there are some detections, but if we plot them against the latitude and longitude, they are completely localized. Either we look at all the detections in the perihelion season, they are all over the Mars, but in the aphelion they are all localized. So, and if we look at the profiles, HCl are on the left, we can see that black are no detections, green are the perihelion detections, and red are these new aphelion detections. And you can see that first, actually, the maximum of HCl are near the surface, not like in the perihelion, where the maxima is somewhere in the atmosphere, and at 15-20 kilometers. The values are smaller. But this leads to the hypothesis that the source is not in the atmosphere, that the maxima is so low near the surface. Tells us that probably it is the surface source. Temperature and water vapor actually are the same as in other cases when there is no HCl. And well, this is actually the main slide. So if we plotted these detections of HCl in the aphelion season, plotted this region near the Albamons, it's actually they are localized in the region where there are a lot of features on Mars. So to the right there are actually new images from the Cassius, from the same Trace Gas Orbiter spacecraft, that show that there are a lot of small scale features. You see the scale of the, well, spatial scale is only several meters, which could be the source of these HCl eruptions. Actually, well, there are a lot of volcanic wars behind this hypothesis, but well, I think only Sasha Sukhimovsky and Oleg Igorevich Kораблев here can say some more details. So the idea is that the HCl is, or chlorine, some bearing species are erupting from these features in this region. Well, and there are some words like dormant volcanism involved, and so on. So in the last slide, from the locations of the aphelion HCl profiles detections, there is a hypothesis that this is connected to the dormant volcanism. There is one like a brave hypothesis that potentially all the HCl detections are connected to this volcanism, that HCl is trapped on the water ice particles, and from the transport it is transported to the southern hemisphere too. But actually I'm not quite sure about this, but anyway. And this is all that I want to say.
That's all. Thank you, Misha. Yes, any question to the volcanic gas on Mars and evidence of ongoing volcanic activity on Mars? Yes, please.
Thank you. Well, you have a lot of observations. How do they fit into the modeling? Are they contradicting to the models, or they are in agreement? Models?
Well, models work the other way. They know the answer and they tune their parameters to fit. So the models predict the perihelion quite well, perihelion observations quite well. But the aphelion, not yet.
One remark, heterogeneous chemistry models. And the reactions behind are debatable.
Well, actually, even the Krasnoporsky model in 2022, he also reproduced, but he tuned some uptakes values.
He did different, yes.
Yeah.
But when you say heterogeneous, does it make difference between, say, dust and ice?
So
what do you need in this chemistry?
There's a
dust or
model
ice?
by Ben Tyson. So, he, as a source of the HCl, he said that it's perchlorates, and as a sink, two mechanisms. Water ice and dust.
Okay, if the discussion is over, or this paper is over, we can maybe move slowly to the coffee break. And thank you, Misha, again, for saving the talk of Sasha. Yes, coffee break.
Dear colleague, we have a change of the chairman now, so I will chair the second part of the Mars session after the coffee break. So we start with the atmospheric presentation. It was made by Denis Belyaev. He presents seasonal water vapor abundance and saturation in the Martian mesosphere and thermosphere.
Good afternoon. Oh, not good. Good morning. Still good morning. My name is Denis Belyaev. I'm from ACS team. On the behalf of our experiment, of our ACS team, let me introduce our study about vertical distribution of water vapor in Martian atmosphere. Speaking about vertical distribution of the water vapor, we of course can connect it with H2O and hydrogen escape from Mars. And we are studying seasonal and latitude variations of this effect, variations of hydropause level, of course supersaturation of the vapor, and impact of dust storm. Previously, in the last century, it was some paradigm how water vapor, how the process of escape of water vapor happens from the surface to the exosphere, and it was considered rather low level, low altitude of hydropause, the point where we have condensation of the vapor, and it was considered that water vapor is mainly concentrated at the lower atmosphere, and it cannot overcome this hydropause level for all seasons of Mars. And at this altitude level, nearby surface, we have photolysis, photodissociation of this molecule, and then molecular hydrogen comes up to the ionosphere, and from the ionosphere, so from the reactions with ions, atomic hydrogen slow and steady escape the planet. And recent, so there is maybe some problem with connection. Shall I don't know. Okay, I will continue. And for last maybe 10 or 15 years, recent measurements established some connection with high water content in the mesosphere and interconnection with hydrogen escape. First of all, from some ultraviolet measurements, it was observed fast variations of intensity of the hydrogen corona. And then more and more studies came with interconnection between hydrogen escape and water enrichment, for example, during dust storm. And then direct measurements from ExoMars trace gas orbiter came with detection of water vapor abundance at very high altitudes, around 100 kilometers. And just recently, 3 years ago, Mike Chaffin he collected together different spacecrafts MAVEN, ACS, and MRO with MCS instrument at one dust storm season, and he found correlations that, for example, this is the trend of dust opacity, temperature, and water ice opacity. Once dust storm happened, it will impact on increase of temperature. It will lead to destruction of the ice clouds, and in parallel, concentration of water vapor was very high at this period and rise up to 100 kilometers. And parallel measurements from the MAVEN ultraviolet spectrometer with Lyman alpha hydrogen corona gives high intensity of this emission. And this loop was very nice proof with direct interconnection between high water enrichment and escape hydrogen from Mars, atomic hydrogen. And that is why in nowadays a new concept of the water and hydrogen escape was established, where water vapor is able to overcome hydropause level and reach altitudes to 80 and even 100 kilometers, where the very strong photolysis, photodissociation gives directly hydrogen, atomic hydrogen production and direct escape of this atom from the planet. And also the interesting situation was with study of the supersaturation of this water vapor, and this study was previously done by Anna Fedorova on the basis of ACS NIR instrument, and the conclusion was that hydropause level and clouds are possible together with supersaturation of water. And the goal of the present paper, our study, is the first direct measurements of water enrichment above 100 kilometers, because previously no one could know what is above 100 kilometers. We study this during dust storm and perihelion, and we use middle infrared channel of ACS. A few words about ACS. It is atmospheric chemistry institute. It is set of 3 spectrometers, and 2 of them, NIR channel and the MIR channel, can perform simultaneous and collocated measurements from solar occultations, and like that we can retrieve simultaneous point-by-point vertical profiles of the structure of temperature, pressure, CO2 density, and of course water vapor. And from these 2 instruments, we are sensitive to water absorption at different bands. At the NIR channel, it is 1.38 microns, and it is sensitive up to 80, 100 kilometers. And most strong band comes from the middle infrared range, 2.67 microns, and here you can see, for example, a clear detection of water vapor lines at the altitude 115 kilometers. And in parallel with these experiments, we can retrieve temperature vertical profile. You can see here comparison, validation between these 2 channels with temperature, then number density of water vapor, and mixing ratio of water vapor, with very good coincidence between these 2 channels. For the moment, we collected our data set for 2.5 Martian years from the middle of the 34 to the end of the 36, reaching different perihelion and aphelion season. On the top we have northern hemisphere with the distribution of these latitudes, and on the bottom we have southern hemisphere. These different colors correspond to different volume mixing ratios from 1 or even less than 1 ppm to more than 100 ppm, which is in red and dark red. Colors, what can we see in both hemispheres? That we can see big enrichment of water at the global dust storm, which happened at the beginning of our mission. Some enrichment at region storms, and stable enrichment at every perihelion every year, and with quite low water value at aphelion season. Previously, we published the paper in 2021 about estimations of this high altitude vapor reaching even 120 kilometers with a quantity between 10 and 50 ppm, and we compared again near and near points with good coincidence with dust season and without dust season at every perihelion. We also compare our measurements with NOMAD data. NOMAD is one more infrared spectrometer on board trace gas orbiter, which also can measure absorption of high altitude water up to 100 kilometers. And here these dense points are from NOMAD. Unfortunately, data from ACS MIR are more rare because of peculiarity of the instrument, but anyway we have good coincidence with parallel instrument working on board trace gas orbiter. Speaking about the next Martian year, 36, we can see, for example, in both hemispheres, individual vertical profile of water vapor. Sometimes we reach even up to 125 kilometers, and then sharp decrease almost to the zero level, for example here, of this content. As I told you that in parallel we can retrieve temperature, and this is analogous temperature field from 10 to 180 kilometers, example from the southern hemisphere. Next two talks by Daria Kosova and Ekaterina Starichenko will be devoted about fruits from this temperature structure. But what is important for this study is that using Clausius-Clapeyron relation for water vapor saturation pressure, using just temperature, we can estimate saturation pressure of water vapor. And it means that we can calculate saturation ratio as ratio of partial water vapor pressure to this saturation pressure. And we plot this map again for the both hemispheres, and dark red and even brown colors here correspond to very high supersaturation, exceeding more than 10 this ratio, and we see that it happens even at high altitudes every perihelion, and also during dust storm as well. It was interesting to study latitude variations of this effect during the perihelion, and since we are in solar occultation, we can divide between morning and evening and terminators, and we see some difference with water vapor mixing ratio and saturation ratio, and we can conclude that we have more water in the evening terminator, like here at the southern hemisphere, but We have stronger saturation during the morning terminator. This difference also agrees with previous ACS near results below 100 kilometers. To conclude, we observe water high abundance reaching 50 ppm and super saturation reaching 10, the ratio, at least up to 120 kilometers during dust storm and perihelion season. To compare, in aphelion season, the content of mesospheric water quantity is less than 1 ppm. Difference is huge. And during southern summer, more water is found in the evening terminator, and stronger supersaturation is observed during the morning terminator. Some work in progress. We try to improve our sensitivity to detect up to 130 kilometers. We compare our data with NOMAD parallel instrument measurements, and also we compare our data with circulation models, GCM, and water, so-called water pump, published, the model published by Dmitry Shaposhnikov. They predict increase of water vapor above 120 kilometers, as you can see here on the map, on the prediction of Dmitry Shaposhnikov using his circulation model. So this is our work for future. Thank you, and questions, please.
Question? Yes.
Well, thank you very much, Denis. Nice talk. Wanted to ask, from the viewpoint of ionosphere, because the maximum of water, the high water which you see, is basically reaches the peak of ionosphere. And we also see that these regions of the dust storm seasons, they affect the ionosphere.
Yes.
Do you have some ideas or some models that can really try to put everything together, ionospheric models, observations, and thermospheric models?
There was also paper from observations and some interpretation in the ionosphere. So where is my list of Maven instrument, Maven on board has enzymes spectrometer, mass spectrometer, and they detect very high water vapor at the altitude 150 kilometers from on the basis of ions, ion chemistry, and they interpret this high value on the basis of ion reactions impacted by a dust storm. I don't remember if I include this or not. Maybe not this paper in my list, but anyway, measurements from enzymes on board Maven could answer on this question, an interpretation of ion chemistry.
Okay.
Stone, yes, it's a paper of Stone. I don't remember. I was thinking that I included. Ah, yes, this one. Yes, ash escape is driven by the seasonal dust storm. Yes, it is ion abundance, and they, yes, they measured because it is during air braking. It was made during air braking of enzymes of Maven, and reaching altitudes 150 kilometers, they retrieve water vapor VMR.
Thank you very much. One more short question.
You have shown predictions 2.67 and 1.38 microns. Yes? For
no, not emission, but absorption.
Absorption.
Yeah.
This is absorption in second absorption, is Berton of first absorption or independent vibrational mode?
Can you?
This means two vibrational
Berton. I cannot say exactly in details. We need to look on Hytran database to look at exact lines.
Okay, thank you very much. I also have one question, but we have moved, so I'll
Okay.
ask later. Okay, the next presentation by Darya Kosova, study of diffusion regimes in the vertical structure of the Martian atmosphere.
Okay. Good afternoon, dear colleagues. My name is Daria. I'm a student at the ACS work team, and today I'm going to tell you about my results at my study of studying diffusion regimes in the vertical structure of Martian atmosphere. Okay. So let's start with a little introduction. In the vertical structure of Martian atmosphere, turbulent and molecular diffusion regimes can be distinguished. Turbulent diffusion dominates in the lower atmosphere, the homosphere, where atmospheric gases are evenly distributed with height, and in the upper less dense atmosphere, namely the heterosphere, molecular mixing prevails, so this causes the separation of gases into layers. A boundary layer where turbulent diffusion changes to a molecular one that is individual for each gas component is called homopause. Commonly, it is located at the range of altitudes from 100 to 130 kilometers. These mentioned diffusion coefficients play a significant role in the modal and vertical transport of atmospheric particles. Unfortunately, there is still no universal method for determining the eddy diffusion coefficient due to its complex nature that combines various dynamic processes, including internal gravity waves. So generally, due to the lack of the experimental data on the wind speed and temperature, literature provides empirical formulas for calculating this coefficient. Also, they're known as parameterization models that are proportional to the corresponding to the correction parameter A, but such models have its own limitations. First of all, this approach is not suitable for the upper atmosphere of the Mars, especially for the transition zone. And second, it doesn't take into account that the correction parameter has seasonal and latitudinal variations. So here you can see the main objectives of this work. First of all, we need to investigate vertical profiles of the molecular and eddy diffusion coefficients in the zone of homopause, then derive the homopause altitude as the point where two diffusion coefficients become equal, and then obtain its seasonal and latitudinal variations. And of course, the dependence of the altitude on the atmospheric density. Here we analyze the vertical profiles of density and temperature derived from the Russian spectromic complex atmospheric chemistry suite on board the trace gas orbiter module of the ExoMars mission. Since April 2018, the middle infrared channel of ACS-MIR has been sounding the Martian atmosphere in the solar occultation mode. we have observations for 2.5 Martian years, and the spectrometer measures atmospheric transmission spectra in carbon dioxide absorption bands near 2.7 microns with a high sensitivity and resolving power of about 30,000. This allows retrieving temperature and density of the atmosphere over a wide range of altitudes from 10 up to 180 kilometers. And also the vertical resolution of the experiment, that is from 1 to 3 kilometers, allows revealing small-scale gravity waves and their characteristics. Such waves arise because of the fluctuations in the atmospheric density in the gravity field of each planet. More details about this will be in the next talk of Ekaterina Strichenko. So here we revised the estimates of the diffusion coefficients in the homopause zone using the approach that takes into account atmospheric gravity waves as a mechanism of vertical mixing. This approach was first tested for even 40 years ago on the Earth's atmosphere, and it's valid for mid-frequency vertical waves and for saturated waves. According to our studies, the wave saturation and breaking was observed at the altitudes from 80 to 140 kilometers. So in this region, we can use such formulas where all the parameters can be obtained from our experimental data. For example, Brain's-Stellar frequency that indicates the stability of the atmosphere. And important note here, we consider only the main harmonics of the atmospheric gravity waves, and the wave number of such harmonics were obtained using the Fourier transform. Molecular diffusion coefficient is defined as the kinetic energy of the molecule that is proportional to the mean thermal velocity and free path of the molecule. And as I said, the homopause altitude is the point where these two diffusion coefficients become equal. So let's move to the results. All in all, we have more than 900 observation sessions, and here you can see the distribution map of the homopause altitude for the southern hemisphere. We can see seasonal variations. For example, in aphelion, homopause reached its minimum values that are about from 90 to 100 kilometers, and in the perihelion season, homopause reached its maximum values that are about 140 kilometers. And this behavior we can see throughout our whole observation period. And CO2 concentration varies from 10 in the power of 10 to 10 in the power of 12 inverse cubic centimeters. Here on the left side you can see the dependence of the homopause altitude on the value of diffusion, and diffusion coefficients varies from 6 times 10 in the power of 6 to 8 times 10 in the power of 7 square centimeters per second. And on the right slide we can see latitudinal distribution of the homopause altitude. Observations were divided into morning and evening hours, and here we can see two branches, red antisymmetric one that corresponds to the perihelion season, and blue symmetric one that corresponds to the aphelion season. And also we can see that in the southern hemisphere the range of altitude is more scattered than in the northern hemisphere. This happens because here in the perihelion season in the southern hemisphere it is summer, so the atmosphere receives the maximum of solar activity, and here in the aphelion season it receives the minimum of solar activity. And similar behavior was found at the INGIMS experiment of MAVEN spacecraft. Here's the conclusion of my speech. So using the wave-induced approach, we found that homopause altitude varies from 90 kilometers in aphelion and to 140 kilometers in the perihelion, with the CO2 concentration from 10 in the power of 10 to the 10 in the power of 12 inverse cubic centimeters. The diffusion coefficients varies around 10 in the power of 7, and all these results are consistent with the INGIMS experiment from the MAVEN spacecraft that was made for 32nd and 33rd Martian years, and their altitude range of the homopause was from 60 up to 140 kilometers. So our altitude range is less captured. Thanks for your attention. I will gladly answer your questions.
Thank you, Daria. Questions?
Please clarify, do you have jump of the diffusion coefficient at homopause? You said below your domination of turbulent diffusion above molecular, but what is their relation at homopause? Continuous transition or jump?
It's continuous, I guess. So in the low atmosphere, we have turbulent diffusion is more than molecular, and after the homopause, molecular diffusion is more than turbulent. So we can say that, for example, here turbulent diffusion is close to zero. So next.
I have one question. Thank you very much. I like this talk. Well, my question is, you used the CO2 observations really
Yes.
to derive that. I wonder, does it make sense, for instance, to repeat with water vapor observations? Will they show the same results, or they show different results?
What do you mean by water vapor observations?
Water vapor observations to really to derive the same things, to do the same things, but with water vapor.
Oh,
Does it make sense at all? So that's probably you can say that no, it makes no sense.
I don't think it's make a lot of sense, because here we talking about we're talking about the carbon dioxide, which is the main gas in the Martian atmosphere, and I don't really think that observations on water vapor will help us to find the homopause.
Okay, thank you.
Okay, thank you very much. One more question. Online, maybe? No. Okay, thank you very much, Daria.
Thank you.
Next talk by Ekaterina Starichenko. 2.5 years of observation of gravity wave activity in the Martian atmosphere from the ATS-TEGO experiment.
Good afternoon. I'm going to tell you about the 2.5 Martian years of observations of gravity wave activity from our experiment. First, remind gravity waves are the waves that appear as periodic oscillations of density, temperature, and pressure. They take their way in atmosphere or in the water. They transfer vertically the energy and momentum from the lower to the upper atmosphere, and because of that they affect the climatology and the dynamics of the atmosphere, and causing such effects as turbulence, as you can all remember from the flying on the plane. Our atmospheric chemistry suite is a set of 3 infrared spectrometers on board a trace gas orbiter of ExoMars 2016 mission. It started its operation in April 2018, and I use the data from the 2 spectrometers from the middle and near infrared ranges, and they have a very high resolution and both work in solar occultation mode, which means that when spacecraft crosses the line of sight of sun, which is outside of atmosphere, it takes its measurement of the sun spectra, and then it takes the spectra of the sun on the line of sight inside the atmosphere, and dividing one and another, we get our final result spectra. They are the examples of the two spectrometers of the spectra, and spectra of CO2, and 2 and 7 microns and 1 and 58 microns. The work is made by my colleagues Denis Belayev and Anna Fedorova, and there is an example of their work. The temperature profiles retrieved, green is for near channel and red is for near channel, and also there is density. Usually in my work I use the temperature profile with altitude, and by the special procedure which I have thoroughly described in my article of 2021, I find the mean temperature profile, the difference of these two temperatures, the envelope of it, which we call the amplitude of gravity waves, Brandt's frequency, which characterizes the stability of the atmosphere. As you can see, at some point the Brandt's frequency of temperature comes near zero, so that means that our atmosphere becomes unstable and waves stop to grow in their amplitude, and the accelerations and the horizontal flux of the vertical flux of horizontal momentum begin to decrease. And there recently we published the results of the two Martian years observations in Astronomy and Astrophysics journal, and in this presentation we prolong our observations to 2.5 Martian years. So there are the results: the seasonal variations of the gravity wave activity, of the acceleration and potential energy of the northern and southern hemispheres. On the first line are depicted the observations we made. The latitude, as you can see, most of the observations are made in the middle and higher latitudes. And then there is the result of the activity. The most activity occurs at southern winter. These high colors mean that the waves are destroyed and they give the energy to the surrounding atmosphere. So that means the high activity. Here we go to the latitude variations of the seasons, and at equinoxes seasons you can see the symmetrical distribution with respect to equator, and in the solstice seasons the maximum of the activity is shifted to the winter hemisphere, the most one in the southern winter hemisphere. And here are the same variations, but with the modeled zonal wind distribution, which is made by our colleague Alexander Medvedev with the help of MAOM MGCM model. And as you can see, the waves are the most activity. The waves are destroyed in the areas with the weak zonal wind, where it comes near zero. And this feature agrees well with the physics of gravity waves, because wave dissipation occurs when the amplitude of waves is equal to intrinsic phase speed of the waves. This is the difference of the phase velocity of gravity waves and wind. So it's easier for wind to be destroyed when the mean wind speed is near zero. And there are also the results of the global dust storm of the 34th Martian year, We have 3 years to compare, 34, 35th, and 36. And as there are not very many observations, we needed some kind of test to see which results we can trust, and for this we used the students' t-test. And by the white color we depict the areas which we can trust with a 95% trust. And the results, we can see that there is decrease of gravity waves activity during the stormy season below 80 kilometers in the northern latitudes, and increase of activity above these 80 kilometers. And these results was previously observed and simulated, and it agrees well with it. And there's also the result that has not been previously observed or predicted, and it's the increase of energy below 80 kilometers in the southern hemisphere. And also the surprise, not in this section, but also there is Venus variations of gravity waves activity from SOAR data. The data was given for me by Elizaveta Fedorova. I made the latitude variations of it. The temperature here, we can clearly see the mesopoles, the amplitude of waves, and the activity by potential energy and accelerations. It is seen that the most activity is in the northern hemisphere, but this result can be not be made by the physics of gravity waves, but because of the observations of SOAR most made in northern hemisphere, and they are more detailed there. So this is the feature that we need to confirm or disprove. A summary that we made greatest statistics for the 2.5 Martian years, and on very high range of altitudes. And we made some seasonal distributions, and the maximum energy of the gravity waves we see at southern winter. There are also the symmetrical distributions of activity in the equinoxes, and not so symmetrical one at solstices. Also the physics of gravity waves is very good compared to the zonal wind physics. And we also made it clear about the impact of global dust storm and their results that we need to confirm in the future. And also there are first results for the SOAR data for latitude, and we also need to prolong this work. Thank you for your attention.
Thank you very much, Katya. Questions? Timo?
Thank you very much. Well, my comment, probably a question. Here you look at the data from the spectroscopy. I know that there are good results from the radio occultations on the gravity waves on Mars. I mean, radio science on Mars Express. Did you have a look at that?
At Mars Express data, yeah?
Yeah.
No, I haven't.
Mm-hmm. Yeah, probably it's worth making because there are about 800 radio occultations. And then they do all this profiling, and in the profiles you see the gravity waves pattern, I mean, deviation from the mean profile. This is the first question, the first comment probably, and the second, very nice to see that you also look into the Venusian, Venus Express observations. Thank you, Denis. Yeah, good, sir. And because you said that mostly the gravity waves, they are located in the northern hemisphere. This is exactly what we see with the Venus monitoring camera, a lot of patterns above the Ishtar Terra. So it's probably, it's the work by Arianna Picciali. So probably it's really, go ahead with this. It's just encouraging note. Thank you.
Thank you very much.
Thank you very much. No question? Okay, online? No? Okay, so we're close the first part of the session. And now the time for lunch. And we return to the conference hall 2 o'clock. Yes, it's 2 o'clock. Okay, exactly. And the next part of the day will be dedicated with surface. It's quite a wide topic, from the surface to the radiation environment of Mars. Thank you very much. See you after the lunch.
Good afternoon. We continue our Martian session, and this subsection is devoted to surface and geochemistry. So we have 20 minutes talks. Each talk is 20 minutes, and please be in time, and maybe 17, 18 minutes to have a few minutes for questions. And the first speaker now is Ekaterina Cholovskaya, clay minerals in the upper part of Nergal valleys, Mars.
Hello, my name is Cholovskaya Ekaterina, and today I want to tell about clay minerals in the upper part of Nergal Valleys, Mars. For this research, the area that includes the upper part of Nergal Valleys was selected. In this region, the clay-rich layers are exposed in the walls of Nergal and Hyodeshir valleys, as well as in the walls, ejecta, and on the floors of some impact craters. Previously conducted research considered different features, but little was done to link the phyllosilicates with the regional geological context. Nergal and Hyodeshir valleys. Previously conducted research consider different features, but little was done to link the phyllosilicate with the regional geological context. So in our research, we focused on analysis clay deposits to understand their formation process and connect them with the geological history in studying area. We use the result of our early research as a geological context. The study area consists of late Nahins hills, which were separated by early Hesperian lava plain. Hyodeshir and Nergal valleys were formed within the early lava plain. Also, we selected young craters because some of them have CRISM data, which we used in our research. So these daytime images of Themis shows CRISM images which we use in our research. Hyodeshir valleys extends for 116 kilometers in studying area from northwest to southeast. It is an isolated fluvial system with no tributaries. In the cross section, the valley have U-shaped shape. Its width increases from 1 kilometer in the north to 7 and 5 kilometer in the south, possibly forming an elongated basin. The depth of Hyodeshir increases from 16 meters in the north to 1 and 2 kilometers in the south. The valley has sharp bends along its interior length, some of which are close to 19 degrees. The main feature of Hyodeshir is the presence of clearly defined layer strata. The stratum with clay minerals lies on the ancient lava flows, and in turns is overlying by young lava flows. Below the outcrops of the bedrock are blocked by losing material, which was formed by the distribution of the rocks of valley walls. The valley floor is almost completely blocked by fine-grained loose material, which forms shallow dunes. A mixture of saponite and nantronite in this layer was identified using spectral data analysis. At the northern end of the valley, the content of clay minerals decreases, but the presence of an absorption band of about 1 and 9 microns in the same layer indicates the presence of hydrated material that is not identified by another bands. The presence of smectites in the walls and ejecta of the crater near the north end of the valley indicate that clay layer continue below the surface. In craters within the early Hesperian lava plain, the iron magnesium phyllosilicates were also identified. They are represented by a mixture of saponite and nantronite. There are no aluminium-rich clay minerals in the studied object. Apparently, in this place, the clay layer was uncovered by impact activity. Also, Nergal Valles cuts through ejecta of at least one crater contain clay minerals. And this suggests that the formation of phyllosilicates predated the formation of valley. Beside on our research results, the following conclusions were drawn. Iron magnesium phyllosilicates represented by a mixture of saponite and nantronite are present in the walls of Hudesha Valley and in the craters. No aluminium phyllosilicates were detected. The clay-bearing strata formed during Nahin. Later, they have been overlaid by Hesperian lava plains. In the late Nahin period, the flux of impactors was still high and large. In large impact events could have caused temporary and local warming, leading to melting of ice and formation and local hydrothermal systems. The available liquid and hot or warm waters could accumulate in the topographic depression of large craters and react with the side rocks to form iron magnesium phyllosilicates. The lack of aluminium phyllosilicates suggests that the side rocks were of ultra basic composition. Thank you for your attention.
Thank you. Questions, please. We have plenty of time for questions.
Can you show the slide of the Herdesha valleys? You here interpreted the young lava flow and ancient lava flow. Why do you interpret this is lava flow? Are there any spectral signature?
Of lava plain? No.
What is the stratigraphic relationship with the layer which is rich in phyllosilicate?
Phyllosilicate is under the Hesperian lava plain. Under, below the.
Thank you very much.
One more question? No? Maybe online? No questions or comments online. Okay, thank you again to the speaker. And we switch to the next talk by Mikhail Ivanov. Time constraints on the formation of valley networks on Alba Patera. Preliminary results.
Друзья наши в Zoom не смогут увидеть.
Good afternoon. In the very beginning, I have to, well, say some words about Jim Head. Recently, he asked me to express his deep regrets for his inability to attend the meeting because of well-known reasons. And we all hope that when the mass will be over, Jim Head will be with us again, either on or offline. Okay, let's go to the talk. So I'll talk about Alba Patera on Mars, which is one of the largest volcanoes on this planet, and about valley networks on flanks of this volcano. Valley networks are well-known features on Mars. They're shown here, and they preferentially occur in the southern portion of Mars. Here, these black short lines, they look like these features here. There's definitely fluvial features that cut by running water. On Alba, here, we also have number of fluvial features, and they kind of off the main major occurrences of valley networks. So it's kind of isolated spot of fluvial activity in the northern hemisphere. And these features formed significantly later in younger Mars comparing to all other fluvial features. So here you show age distribution of valley networks in southern hemisphere, and here this dot corresponds to age of valley networks on Alba Patera. So what kind of questions we try to address in our study? So what are the age relationship between Alba Patera valley network and lava flows on Alba? Who was older? What was older? What was younger? How topographic configuration of Alba Patera controlled and controlled the distribution of fluvial features, and how this configuration might put some constraints on mode of the origin of fluvial features. What if these fluvial structures, fluvial features, valley networks on Alba, marks transition or transient warmer and wetter conditions on Mars, or maybe these features formed by interaction of ice and hot volcanic material. So what how Alba Patera looks like. So this is Alba Patera. That's a shaded relief image of the volcano, and it consists of several distinctive parts. Main body here, two lobes on western and eastern side of this main body, summit plateau and summit dome with calderas. Distribution of slopes, because slopes play important role in distribution of fluvial activity. So this image shows distribution of local slopes, and you see that majority of Alba is characterized by very shallow slopes, and very tiny portion of Alba has have slopes more than 4 degrees. So these green and yellow colors correspond to this range of local slopes. And these blue lines here show distribution of all fluvial features, valley networks on Alba. So we mapped about 5,500 fluvial features here. They occur on all sides of Alba and prevail on the northern flank of the volcano. And they start to tend to begin at the edge of the summit plateau. Length of this thing. So these fluvial features, although they might resemble rivers, in fact, they are much shorter. So this distribution of lengths of these valley networks, this plot show the comparison with terrestrial small rivers. So this is small rivers from Moscow district, tiny rivers like Gzhelka, Setuny, tiny brooks. And we know that these are formed by surface runoff and precipitation surface runoff. And valley networks on Alba much shorter. In fact, they represent short ravines, short gullies on flanks of Alba. What components these valley networks consist of? Actually, there are two main components of valley networks on Alba. First of all, these are narrow channels here, shown in black, and they also show these blue areas which resemble narrow U-shaped canyons. These features, the channels and canyons are alternating. Red lines here show edges of lava flows. So, having two parts of channels on Alba, we might think that channels formed by running water, downcut erosion, and canyons might correspond to local broadening of fluvial systems where erosion was mostly side erosion. So if this hypothesis is correct, then we should expect systematic changes in local slopes between narrow channels and broader canyons. But the topographic configuration of a, I don't know why. Wait a minute. Topographic profile along one of the channels shows that there is no systematic changes in slope. So this is basin, channel, basin, channel, basin, channel again, and this is general slope of this system, and this is the trended topo of the channel, which shows that there is no systematic changes between slope within channel and basins. So there was no systematic changes in regimes of erosion. Now, where on slopes these channels are distributed preferentially? So this, again, blue lines shows distribution of valley networks. Green, yellow, and red shows the distribution of slopes. And we see that these channels occur exclusively within this range of channels. They do not continue downward in areas where slopes are shallow. So this distribution of channels poorly, if at all, consistent with prolonged fluvial activity caused by the surface runoff. Now, what the age relationships between lava flows on slope flanks of Alba and the channels? So here in these pictures, you see that the channels either controlled by lava flows here, or they cut lava flows. So in both cases, fluvial features on Alba are younger than lava flows on flanks. What's the age of lava flows? We cannot confidently estimate age of fluvial systems themselves, but we can estimate age of lava flows that control distribution of fluvial features. So these ages, absolute model ages, correspond to several lava flows. So here is a summary of these determinations of ages. So these red dots correspond to ages of lava flows on flanks of Alba, and all channels, all fluvial features on flanks of Alba are much younger. So they definitely postdate the major episodes of volcanism on Alba. So summary. So the valley networks on Alba are abundant. So we must have numerous sources of water, probably packs of ice or something like this. So they prevail on northern flank. So water sources were not evenly distributed across Alba Patera. So they consistent with or indicative of preferential deposition of water from on the northern flanks of Alba, probably transport of water from northern lowlands to this elevated feature of Alba. They're short. I saw these things. So the sources were kind of limited in capacity of water. So water transportation from atmospheric water transportation was not very effective, and this might be consistent with is a regular supply of tiny amounts of water, or with periodic supply of larger amounts. Steeper slopes control the distribution of valley networks. So that again supports limited reserves of water in the source area, poorly consistent with valley network formation by surface runoff, and suggests that Alba fluvial activity has been caused by interaction of ice rich accumulation with localized heat sources. So we see no evidence for prolonged precipitation, surface runoff, and we see no evidence for any significant changes in climate condition on Mars during formation of valley networks on Alba. These valley networks postdate all visible lava flows. So this suggests that visible lava flows did not trigger formation of valley networks. So probably heat sources were hidden below the surface of Alba, and probably it was these sources were not related with effusive volcanism on this volcano. Maybe it was were subsurface dikes or shallow magma reservoirs. Lack of, at least now, we have lack of evidence for multi-stage formation of valley networks on Alba. So heat sources were provided by a rather short activation of magmatism in Alba. So, and we, estimating age, we might say that absolute model ages of lava flows on Alba provides a lower time limit of fluvial activity and magmatic activation on Alba about 1 billion years ago. That's what I have. Thank you.
Thank you.
Questions?
Questions, please. We have many time in advance, so for some discussions. No, and maybe online. No comments online.
Свободен.
Sorry?
Свободен.
Yes. Thank you again, Mikhail Ivanov. And we switch to the next speaker, Jun Chu. Sorry if I'm incorrect. Jun Chu. Oh, okay. Morphological features along the fixed contour lines indicating water level changes in the Holden crater on Mars.
Good afternoon, everyone. I'm from Lomonosov Moscow State University. Water on Mars is a very interesting question. Now I will talk about the water history of the Holden crater on Mars. The study area is the Holden crater is low. The Holden crater is located in Marginifer Delta. The diameter is 154 kilometers. It formed in translation from the Noachian to the Hesperian time. Its formation distributes the water from the Uzboy valleys. There are many layered deposits indicate the station of water body in Holden crater. This is the correlation of the outcrops of layered water layers deposition. This is a clean rich in phyllosilicate. The Uzboy valleys broke the rim of the Holden crater. The profile of the Uzboy valleys, there are the 1,200 meters indicate the inner terrace of the Holden Uzboy valleys. And in this profile, there are two key points. One is the 1,840 meters, and the second is minus 2,160 meters elevation. So there are this key point indicate the station of water body in the Holden crater. We choose these three elevation because to draw the closed contour lines. Because the closed contour lines indicate the equipotential level of protective water body. This is shows the three closed contour lines in Holden crater. The first minus 1,200 meters correspond to lower terrace in Uzboy valleys, which influenced the Holden crater. This elevation shows the maximum possible water level in crater after Holden rim branch. It is closed because indicate there are no outflow from the Holden crater. Because maybe it's a closed water body. In the northeast and the southeast portion of the Holden crater, the contour lines follows the rim of the Holden. It indicates there are less geological process. But in this side, there are the contour line destroyed towards the center of the Holden crater, indicate there are erosional or depositional process occurred in this side. In the southern portion of the crater, there are also destroyed contour line, indicate there are also a geological process occurred in this side. The layered deposits, outcrop of layered deposits located in this side, there are also deformed contour line. The morphological features around the Holden rim branch, the channels in this side indicate before the Holden rim bridge, there are also many waters entranced, overspilled into the crater when the water level in Uzboy Lake reached minus 350 meters elevation. The alluvial fines here overlays the channels, suggest that this alluvial fine formed later than the water overspill into the Holden crater. And the stratigraphic relation showed that this side layer deposits occurred was cut by the flood channels. These flood channels. This is show that the water level before the Uzboy rim branch have reached the elevation between minus 2,160 and this elevation. The next, in the southern part of the Holden rim, there are many features shows the water drop. First, there are many residual delta fine. I have drawn these inverse ridges on the fine surface. And the landslide. The landslide is cut many of the channels. At the head of the, in the front of the landslide, there are also stepped front alluvial fan, which indicate the drop of water. This fine was cut by the Uzboy channel. This showed that this fine formed before the Holden rim branch. And the outcrops of layered deposits shown there have eroded front. This showed the after the Holden rim branch, the water eroded the front of the alluvial fan. Again, the fines have two elevations stepped. The lower fine formed after the Holden rim branch, we interpreted. The higher fine formed before the Holden rim branch. This is according to the stratigraphic relationship and the relationship with the contour line. The erosional features have have the analogy of the terrestrial analogy. This is in this side we can see the erosional front of the Holden rim branch fine. In Crimea, there is the river Uzum, the eroded limestone Upper Ura shows the analogy of this landform. And the toe of the alluvial fan here have more eroded than this side. So it indicates the water flow is from the Holden Rim branch here, from here to there. So this eroded more than here. In the to the east of the Holden Rim branch, in the southern part of the portion of the Holden Rim, there is also many features. Number 2 shows the alluvial fans from the southern part of the rim. These they showed there are no erosional front of this alluvial fan. It is indicated that the fans was formed before after the Holden floor was dried. The minus 2,160 contour lines was moved towards the center of the crater. This showed that there may be have occurred the tectonic uplift here. So the shoreline was moved towards the center of the crater. The parallel ridges shows the parallel shoreline. And the tectonic movement caused the fracture on the floor of the Holden crater in the southern part. In the other side, the northeast part, they are followed by the ring of the Holden crater. This shows that there are gelasse or bridge deposit from the standing water. And the cliff-like features formed by the shock of the impact. There are two broad impact craters here. And the contour line shows there may be a later alluvial fan activity. In the west part of the crater, there are many alluvial fans. We have interpreted these fans are controlled by the base level changes. So this is the first sequence. This is second sequence. These maybe have progradation or cliniform. In petroleum geology, cliniform is very good collector for oil. There are also in the northern part of the big trough. The big trough was covered by the alluvial fan. So the trough was formed after the alluvial fan formed after the trough was formed. This also shows that when the water level lower than 2,160, the water flow from the Uzboy changed to erosional region. Here. The chronology we have done for the southern part of the crater floor shows by morphology, the southern part of the floor can be divided to two parts: the western roof plains and the eastern dark plains. The eastern dark plains have showed more older age, 3 and 6 gigayear, and the western roof plains shows two model A ages, 3 and 1, and 2 and 2. This may be according to the erosion resurface process here occurred here. And the model age of the Holden Bridge fan shows a more younger age. This indicates that the water activity from Uzboy continued to even later to Amazon times. This is a correlation chart. The first, the water level in Uzboy after the formation of the Holden impact crater. The Uzboy Lake formed. The water level reached 250 meters, with the seepage, the entrance water from to the Holden crater. The water level in Holden Lake may be a little dropped. After the dam bridge, the inlet entrance was very big. In this time, the fluvial activity around the Holden Rim begin maybe even earlier or even later, but they continued even later, even younger than 2 and 2 gigayear. In this time, the water level in Holden crater was uplift to between the 1,840 and 1,200 meters, and steeply dropped with 2 steps. In the fracture tectonic in the southern floor have a very long history formation, and the impact occurred on the floor of Holden occurred even later. It's very young impact event. So this we can see the fluid activity around the Holden Rim alone have continued a very long history, and the time of the Amazon time may be the climate may be even wet and hot. The conclusion is here. After the water vibration, the maximum water level can reach this elevation. And some alluvial fan have a long history formation. After the Holden water dropped to this elevation, the water flow has have changed to erosion region. The entrance of southern plains was formed in this very older age and have 2 times of resurfacing. And the impact on the floor of the Holden crater was very young, and formed after the water level dropped below this elevation. Thank you very much.
Thank you. Questions, please. Yes.
Nice talk, thank you. Question about fractures on floor of Holden. These big graben-like features on the floor of Holden. So you interpret this as a result of uplift?
Uplift.
Maybe it was subsidence of the floor?
I have what subsidence floor maybe occurred in the even east part. In this side, the load of this no. Was in this side, there are Japanese here. Maybe this occurred by the law, gravitation. And the other side, there are no evidence about the law, gravitation law. So I interpret this uplift. So the water shoreline is moved gradually to the center of the Holden. Like this is a barrier shoreline gradually towards the center of the Holden crater. So uplift maybe occurred in this part.
That's very strange because this uplift is pretty close to the rim of Holden.
Yes.
Why?
No, I have tried to interpret the charisma, but there are no charisma cover here. I think there are no intrusion, because the albedo here is dark. In the other side of the, for example, Ladon, valleys. There are also dark, low elevator location in even there are publication interpreted this is maybe in phyloclastic or in tools,
Okay.
dike,
Okay, yeah, thanks.
magmatism.
Yes, Dima.
Thank you. A general question. I wonder if a similar process are seen in other craters, for instance, in other places, because we see a lot of lakes, paleo lakes in the craters. So do you see similar processes of changing water level, etc., etc.? How they correspond to that?
Yes, example is just northern to this crater Elizabeth. There are also Gypres, paleo lakes, and branch rim and entrance water to the crater and formed the very famous fan delta, river delta. Here, just to the north of Honecker. Last year I have do the presentation about it.
More questions? We still have time for discussions. No? Online? No one? Okay, let's thank again. And we switch to the next speaker. Next talk by Igor Kulik, Constraints on the viscoelastic properties of the Martian mantle by the Chandler-Wobble period.
Good afternoon, ladies and gentlemen. To introduce you in this topic, I'll start with definition of the term Chandler-Wobble. Chandler-Wobble is a free mode of a polar motion. It is a particular case of renutation of the planet. For Mars, excitation of Chandler-Wobble is related to the seasonal mass exchange between polar caps. For the first time, Chandler-Wobble period was detected with quite a good accuracy from radio tracking observations by missions Mars Odyssey, Mars Reconnaissance Orbiter, and Mars Global Surveyor. Period of Chandler-Wobble is 206.9 plus minus 0.5 days. My talk consists of two parts. In first part, I'll tell you about construction of Martian elastic internal structure models, and in the second part, I'll tell you about introducing elasticity in our models, calculation of Chandler-Wobble period, and main results. Let's start. To build models, we should define some constraints that our models should satisfy. These constraints are geophysical constraints, such as mass, radius, moment of inertia, and Loft number. And also constraints are seismic data that were recently obtained from the seismic experiment by InSight mission. These data are crustal thickness, density, and also core radius. Moreover, last year there was a paper by Samuel et al. Where scientists discovered partially molten layer above the core mantle boundary. So the evaluation of core radius became 200 kilometers less. There are a lot of chemical composition models. In our work we use cosmochemical J-Bus-Chem model. This model is based on the analysis of the composition of Martian meteorites. Main assumptions of our modeling are the crust density is constant, the crust thickness is 50 kilometer, and we also vary parameters such as crust density in the range 2.8-3.1 gram per centimeter cubed, iron number between 18 and 25, and we also vary core radius and core density. Core density we vary through varying sulfur content of the core. The method of models construction is taken from paper Jarkov-Gudkova 2005 and from articles Bedcafe 1997-1998. We take data on mineralogical composition and phase transition boundaries. In these articles, authors provided an experiment. They took samples of J boson K composition and put them under high pressure and temperature. So they obtained mineralogical distribution along the areotherm, and you can see this distribution on the right side of the slide. We evaluate density for each mineral at fixed temperature and pressure from the Birch-Monogam equation by the dichotomy method. In this way, we obtain density for each mineral, and then we calculate density of the mixture in the approximation of additivity of partial volumes according to formula that you can see on the slide. On the graphs you can see on the upper graph distribution of minerals, and on the bottom graph distribution of density that we obtained. In this way we obtained density distribution along the pressure, and to obtain density distribution along the depths we need to use mass equation and equation of the hydrostatic equilibrium. Then we calculate velocity distribution. For the crust we take velocities constant and equal to 7 and 4 kilometers per second for compressional and shear velocity. That is inconsistent with seismic data from inside mission. For the mantle, velocity is calculated by formula of the third order finite strain theory that you can see in the left side of the slide. And for liquid core, we calculate velocities by formula that you can see in the right bottom corner of the slide. On this slide, you can see distributions of different parameters that we obtained for one of our model. In detail, distribution of temperature, density, pressure, compressional and shear velocities. In order to compare models that we built, we need to also calculate moment of inertia value and Loft number K2 value. Moment of inertia, we use formula on the slide. And to calculate Loft number K2, we use a system of 6 differential equation from article Alterman oscillation of the Earth, and these equations are presented on the right side of the slide. So we built a lot of different elastic models. You can see them on the slide by single dots for different iron numbers, for different Loft number value on the x-axis, and for different moment of inertia value on y-axis. Thick lines represents areas of acceptable values, and thin slope lines represent lines of constant values of crust and core densities. As you can see from the left graph, models with iron number 22 have quite a low crust density with values in the range 2400 to 2700 kilogram per meter cubed. That is lower than than data from the InSight mission. But it is not the case for models with iron number 20 and 18. These models satisfy all the constraints. In this way we build elastic models, but the real state of the planet differs from the elastic state, so we need to introduce inelasticity in our models. We use Andrade rheology because this rheology is widely accepted in recent works on planetology. In this rheology, there are two parameters that we don't know. This is Andrade parameter alpha and the viscosity distribution eta. Moreover, an additional issue is to evaluate viscosity in melt layer that was recently discovered. So we provided additional numerical experiment. We constructed a lot of models with different viscosity in this layer. And viscosity is shown on the x-axis. And for these models, we calculated value of log number K2, which you can see on the y-axis. And as you can see from the graph, there are two states of this layer: the elastic state on the right side of the graph and inelastic state on the left side on the graph. And because inelasticity introduced in models only through log number, so we are free to choose any value of viscosity of this layer from the left side. And to avoid numerical mistakes, we should not take values from transition and near zero values. So we decided to choose value 10 to the 9 Pascal second. In our model, we use piecewise constant distribution of viscosity. It is presented on the slide. By blue line, you can see density. Viscosity distribution is presented from right from the diagram. On the slide, you can see different layers: crust, upper mantle, middle mantle, lower mantle, melt layer, and core. Parameter of model of viscosity model is viscosity of the crust at 0. Then we calculate Chandler-Wobble period according to formula that you can see on the slide, and we obtained dependence of this value on parameters of rheology, Andrade parameter on the x-axis, and viscosity parameter. Exponent of the viscosity parameter is presented by numbers on the slide. Viscosity parameter is expressed in Pascal second. Lines represent area of acceptable values, and as you can see, models that satisfy observable value of Chandler-Wobble and also have a reasonable value of viscosity parameter have Andrade parameter alpha in range 0.3, 0.5 and viscosity parameter in range 10 to the 21, 10 to the 24 Pascal second. That brings me to the end of my talk. On the slide you can see main points that we discussed above in detail. We obtained distribution of density, pressure, seismic velocities. We built model of Mars that are consistent with all constraints. We introduced Andrade rheology. We also considered the melt layer, evaluated the viscosity value for this layer, and we calculated values of Chandler-Wobble period for different models. Thank you for your attention. I'm ready to answer your questions.
Thank you. Questions, please.
Thank you for your talk. It was very good that you brought your assumptions in the very beginning. And one of these is crustal thickness, right?
Yeah.
50 kilometers.
Mm-hmm.
But it is mean crustal thickness?
Yeah, we...
Well, we have lots of variation in crustal thickness on Mars. We have lowlands in northern hemisphere, to have Tarsus, to have two huge basins, Argyre and Hellas. How these disturbances in crustal thickness might affect your model? Or it's just unimportant thing?
We just calculated spherical symmetrical models.
Spherical symmetrical models are calculated. It's not impossible to distinguish between crustal thickness using the K2 Love number. So it's not good accuracy to see the tomographic models.
Second question, Oleg Igorevich.
Fine work, thank you. I have a practical question. From this kind of models, could you constrain the contents of volatile elements in the mantle or the crust, like sulfur or chlorine? Not just iron.
We didn't study this yet. We just study sulfur content and hydrogen content of the core to vary the crust. But for mantle, we didn't study it yet.
I have some short question, general. Does similar chamber wobble-like oscillation excited when there is a hit of planet with asteroid, or it's too weak effect?
Sorry.
Значит, к вам вопрос. Иванов. Okay. Nobody knows. It should be some effect, but it's interesting qualitatively. It produce observable wobbles.
Additional question. Is there any possibility to check your results with some observational data?
Only additional seismic experiments can be. I'm not sure.
Dima, yeah.
I have a follow-up question to this. Do the observations by InSight have any relevance to this in building the model, checking the results, etc.?
We just used seismic data from InSight mission as constraints for models.
Okay. No more questions. As usually, no online questions. Thank you again, Igor.
Thank you.
And we move to the next speaker, Anton Salnikov, but I was told that is another person, Alexei Batov, sorry.
Is absent today. My name is Alexei.
Okay, Alexei Batov, challenges and approaches in constructing Mars magnetic field models from satellite data?
Yes, thank you. About Mars magnetic field measurements, first of all, that are made by automatic interplanetary stations. Some history here. The first Mariner 4 detected a very weak magnetic field signal, which didn't support the hypothesis of a global field, but he flew by Mars at a distance of about 10,000 kilometers. After that, Mars 3 flew at about distance 1,500 kilometers and detected, it was told in one paper that it has detected magnetic field in the Martian crust, but these observations were very uncertain. The great information about Mars magnetic field came from MGS mission. It confirmed the hypothesis that there is no global magnetic field on Mars. A lot of observations have been made first at the first step of the mission about 1,000 elliptical orbits from 85 to 170 kilometers, and then it was mapping orbiter stage when when the orbit was about circular, and a lot of data served us to construct many models of crustal magnetic field. A very strong magnetization of the southern hemisphere was detected during this mission. And nowadays we have Marvin mission. It started 10 years ago, and provides new data on the magnetic field of Mars at different altitudes. It refines magnetic field models by combining with MGS data. It has 2 fluxgate magnetometers on board, and it has non-polar elliptical orbit with a pericenter about 150 kilometers. And minimal altitude about the ellipsoid is 117. I should say about one more orbiter. It's Taiwan 1, but there is only a few amount of data, and we can find them only from the papers from Chinese colleagues. But we hope that we will have more data on this orbiter later too. Mars magnetic field measurements by landers. The first measurement of the magnetic field on the planet's surface was made by InSight mission, and it turned out that it was 7-10 times stronger than predicted by all the models that were based on the orbital data. Maybe due to the lack of data on local anomalies, and maybe on because there are small-scale structure that couldn't be observed from such distance. And Giron mission provided data, and the magnetic field was 10 times weaker than predicted by models based on the orbital data. And as I said, low altitude daytime data from Taiwan 1 orbiter are also publicly available, but not a lot of information. In the picture you can see the model from the last global model from Vizorek work. And at the right side of the figure, you can see the area that was investigated in this work. It includes the landing sites of Jurong and Inside. About Maven data sets, we worked with the data from we understood that we should work with real observed data, not with the modeled data. And what we can find at the Planetary Data System website, it's 3 packages: auxiliary package, calibrated data package, and key parameter data package. About key parameter data package, is the data is presented in physical units and averaged at a uniform frequency. Up to altitude of 500 kilometers, data is recorded at a frequency of 1 measurement per 4 seconds and above 1 measurement per 8 seconds. In addition to measurements to the spacecraft magnetic field time, the position, the in situ data provides key parameters and ephemeris information from both the spacecraft instrument measurements themselves and the SPICE libraries. So we have in this package 235 features or columns. And the number of rows, if we take the data from 2014, is about 38 millions of rows. Now we so we have additional information to think about how to implement it in further models. Measurements and orbits. Maven spacecraft is has an elliptical orbit with the altitudes varying from 116 or 17 kilometers to 6,500 kilometers. And until 2021, data were collected at lower orbits, less than 150 kilometers, and now it's operating on a little higher altitudes. And measurements are available in the range from 75 degrees south to 75 degrees north. From MGS, we have data for these missing regions. We should notice that the observed magnetic field values are a superposition of the external magnetic field and the constant magnetic field of the crust, and it's really a trick to decompose these fields in such manner. At the figures, we limited the data sample to an altitude of 500 kilometers because we're interested in the lowest altitudes. At the figures top are the number of measurements, and if we will talk about unique orbits at the bottom, we have less data over the surface on Mars. At the top are the altitude profiles by time, and at the bottom we can see that at the bottom 3 magnetic components, and we can see that at high altitude it becomes very low, but we still have this external magnetic field. So in this work we discuss about data up to 500 kilometers. When we structure our model, we choose a grid on which we will work. We used two grids. One is SRAG. It's a spherical rectangular equal area grid from work of Malkin 2021, and compared it to a standard rectangular grid Driscoll Healy 2. Grid step is 0.5. The figures, it's a comparison of these grids, so we have we will have more differences near the poles. At the area of equator we will maybe have the we can say same situation. One more slide about difficulties in data, daytime and nighttime data, and we should divide them. Nighttime data exhibit significantly lower noise level than daytime data because they are less susceptible to external magnetic disturbances. So the nighttime data are preferred for modeling the lithospheric magnetic field. Daytime data can be significantly distorted by solar activity and currents generated in the ionospheric of Mars. In our work we defined nighttime data as measurements between 7 p.m. to 5 a.m. Local spacecraft time. We took it from work from the last model of 2019 from Langley model, but we can, for example, take time interval from 8 p.m. to 4 a.m. can be used. It was suggested in work by Mittelholz, but we'll have less data, but they will be more clear. Also, we can calculate the angle and take data when we don't see, when the spacecraft doesn't see the sun. But when we're restricting the sample to only nighttime data, we get less data, and we have, for example, we have 31 missing values in our 14,000 nodes of our grid for the selected region. The figure is an example of the using top. We use only nighttime data, and we see that with the distance we see that we can approximate it with some curve, and we see it clear, but we have more disturbed data when we use both night and daytime data. We use as approximation method to construct the model. It's one of the variants of the linear integral representation method. The field potential is represented as the sum of the potentials of a simple and a double layer located on certain carriers below a given relief. It allows the creation of highly accurate approximations of the magnetic fields based on large volumes of satellite data and further transformations of the model field. The problem is reduced to finding a stable approximate solution of system of linear algebraic equations. We use both local version of this method and regional version. Matrix elements have relatively simple analytical formulas for calculating for local and regional version. In regional version we have an elliptical integral of the first kind. Because of that we will have more computational time for this, but we try to make our algorithm fast. We program calculations in a vector form and try to parallelize them with number and other methods. Here are the results of S approximation method and analytical continuation to a single altitude. Because after the filtering the data, we have data on different altitudes. It's really a task to go to one single altitude, and here you can see the results. The approximation is made in good. The approximation accuracy is good, and on the figures on the left are the initial measurements of B radial at altitudes closest to 150 kilometers. In the center is the analytical continuation and the difference between the initial data and the results of continuation. Here is our algorithm. With the steps, grid formation, data filtering and regrouping, data sampling, S approximation implementation, and evaluation of results and field transformation. And if we are not satisfied with the result, we can go to previous steps. So in conclusion, we can say that modular design can facilitate the implementation of an algorithm for building Mars magnetic fields models from satellite data. A clear specification on the parameters allow iterative refinement of the algorithm output at any stage. The refinement procedure allows reversion to previous stages in case of unsatisfactory results. Building accurate models of the Mars magnetic field requires careful consideration of the complexities of the field, to use large data sets, and we're dealing with noisy data and limited spatial resolution. And the key features of any algorithm is the choice of a suitable approximation method, and once again the choice of samples of data with which we work. And it was noticed in many latest work that when we try to we should this step of selection of samples is one of the main important because it influences to our models, and the refinements of models of latest models was mostly by a good creation of data. Thank you very much.
Thank you. Questions, please. Yes.
A very small note in addition to the first slide. Phobos 2 missions have a magnetometer too.
Yes, but the results were very uncertain, so it's discussed if we can get some information from it, but yes, it was noticed that it was some detections you can see Mars 3, Mars 2, Phobos and Phobos 2.
Okay. Lev Matveyevich.
I have very simple-minded question. You want to develop model of the crustal magnetic field, but in all measurements, you have the mixture of the crustal magnetic field plus currents flowing in ionosphere, which is rather close, introduced by solar wind, which is very variable. How you distinguish one from another? What is your procedure? Just to get the crustal.
At this work, we use nighttime data, so we try to exclude solar activity, and we have we have different approach to have data on the lowest altitudes. We tried samples at not lower but at altitudes where we get models of our distribution, and you are right. It's difficult to decompose. There are models. Maybe we will. There are models of Mittelholz. They have a model of external magnetic field, and at some works they try to just exclude from the magnetic field external field from this model, for example, and investigate this part. Well,
use data for the night side. You may be right, because the night side atmosphere is very weak and probably with very weak currents. But for this side, it's really important, the induced magnetosphere of Mars.
Yes. So, but we have less data.
Okay. Thank you. Thank you to the speaker.
Thank you.
And the next talk will be online. Yes. Will be given by Hugh Lee. Statistical properties of plateau-like turbulent spectra in the Martian magnetospheres. Maven observations.
Hello? Can you hear me?
Yes.
And can you see my screen?
Yes.
Okay, thanks very much. Good afternoon, everyone. I am Hui Li from the National Space Science Center, and this is our institute here. And today, my topic is about the plateau-like turbulence spectrum in the Martian magnetosheath. And Dr. Jiang and Professor Chi Wang and Daniel are the co-authors. And my talk contains three major parts. First of all, I would like to give a very brief introduction to my talk. This picture shows the causal chain of space weather processes. And in the causal chain of space weather processes, the magnetosheath serves as the boundary of the interaction zone between the solar wind and the planet, which playing a crucial role in the transfer of solar wind energy to the Earth. And the turbulence is an important pathway and a key indicator of energy conversion and dissipation, making it significant for understanding the energy transfer processes. In the solar wind, the PSD of magnetic field exhibit several different power law spectra like this. And this include, for example, the -1 spectra in the energy injection range, the -5/3 spectra in the MHD inertia range, and the -2.8 spectra in the kinetic dissipation range. The characteristics of the turbulence in planetary magnetosheath undergoes some changes, and using the relevant spacecraft observation, we have conducted corresponding studies on turbulence in the magnetic sheets of planets in the solar system. And for example, this is the result for the Mercury, and this is the result for the Venus. And of course, we have the study on the Earth, and we also have the Mars, and the Jupiter, and the Saturn. And despite the extensive research on planetary magnetic sheath turbulence, there are still some issues that require in-depth exploration. As you know, the solar wind plasma and the neutral atoms undergoes a charge exchange processes, turning the neutral atoms into charged particles, which are then captured and accelerated by the solar wind electric field. This process is known as the pickup process, and these newly formed particles are referred to as pickup ions. Compared to the Earth, the density of neutral hydrogen in the Martian magnetic sheath is 200 times higher, providing an excellent environment for the formation of pickup ions. These pickup ions have a ring beam velocity distribution function and a significant amount of free energy, which is highly conductive to the excitation of waves. And in this talk, we will talk about the impact of these ions on turbulence, which remains insufficiently studied. The observations are mainly obtained by MAVEN and Tianwen-1 satellites. During 2015 to 2019, we have analyzed nearly 4,000 cases in the Martian magnetic sheath. Then I will show you some results. And usually, the turbulence spectrum in the Earth's magnetic sheath have one breakpoint at a kinetic scale here. However, the PSDs in the Martian magnetic sheath usually present an additional break at a frequency well below the typical kinetic scales. For example, the PSD breaks into 3 parts with different spectral indices, which is minus 1.8 and minus 0.3 and minus 3. And we define such PSD as a platoon-like spectrum. And from the ion velocity distribution here, it can be observed that this event is accompanied by pickup ions, and the ratio of transverse to compressive fluctuation power increases to about 5, indicating the presence of transverse waves here. Additionally, the waves propagate along the direction of the background magnetic field and exhibit left-hand circular polarization, which indicate that these waves are proton cyclone waves. Platoon-like PSD is very common in the Martian magnetic sheath. We have analyzed nearly 4,000 cases, and the occurrence rate is about 60%. And furthermore, the occurrence rate correlated well with pickup ion relevant parameters. For example, it peaks at when the pickup angle is close to 30 degrees. This is positively correlated to the plasma density and negatively correlated with the plasma beta value. These characteristics are consistent with the PCW mechanism. For example, the Coy and Gray found that the energy of PCW saturates when the pickup angle is 30 degrees, while the Anderson and Fossilia pointed out that as the plasma beta increases, the ion cyclotron instability gradually dissipated and transports to mirror mode instability, causing the decrease of PCW. And in addition, the occurrence rate of platoon-like PSD is highly at the aphelion and lowest at perihelion. This is inversely correlated with the sun UV radiation, which aligns with Harada's observation that the occurrence rate of PCW also decreases with the EUV radiation. And in contrast to the stronger fluctuations observed in the foreshock region here, the occurrence rate of platoon-like spectrum in quasi-perpendicular magnetic sheets is higher, which suggests that the PCWs are more likely to be generated locally rather than propagating from the upstreams. And from the joint observations, we found that the turbulence PSD observed by MAVEN here in the upstream solar wind and by Tianwen here in the magnetic sheets are totally different. The solar wind turbulence spectrum is here, and the spectrum in the magnetic sheets is here, which is a platoon-like. This different result indicates that the platoon-like spectrum is caused by some locally processes, which is not from the upstream solar wind. This is a very good jointly observation event. And they also produce the, this example shows that the modulation effect of pickup ions on the PCW. We have two intervals. One interval A, we have more pickup oxygen, and this interval we have less pickup oxygen. At the same time, the second slope of the PSD steepens with the abundance of pickup oxygens here. And furthermore, we conducted a PIC simulation, which confirmed that when the pickup oxygen is abundant, the amplitude of the PCW is relatively small. For example, the red one shows there are a lot of pickup oxygen, but the black one shows there are less pickup oxygen, and this gives the wave amplitude here. And furthermore, we have a statistical result that the amplitude of PCW is relatively small, verifying the theory that heavy ions suppress the PCWs. And of course, we believe that the PCW is an important mechanism causing the platoon-like PSD, but there are not the only mechanism. And for example, this is an example of platoon spectrum here, but we have no transverse waves here, and no waves shows indicating the PCW. However, we also found some fast mode and slow mode waves during this event. So rather the presence of fast mode or slow mode of magnetosonic waves can also cause the platoon-like spectrum. Okay, the last give a very brief summary. As you know, the platoon-like spectrum are ambiguous in the Martian magnetic sheets. We have analyzed about 4,000 events, and the occurrence rate is nearly 60%. And there exist strong correlations between the occurrence rate of platoon-like PSD and the pickup ion related parameters. And the pickup ion can modulate the platoon-like spectrum through PCWs. And substantial presences of pickup oxygen can suppress the PCWs, which is driven by the pickup hydrogen, resulting stability in the slope of the platoon spectrum. I think this is all of my talk. And for more details, please found in these two references. Thank you.
Thank you. Questions? Yes, Lev Matveyevich.
Thank you for very interesting talk. I have question about interplanetary magnetic field because its influence on the shape of the upstream shock. Do you see any influence of direction of interplanetary magnetic field on the shape of the spectrum in magnetospheres?
Okay, very good question. And we have shown that the waves are generated locally, but not from the upstreams. And we also have not check the the strength of magnetic field to this wave generation. And maybe we can do it in the future. Thank you.
Yes, one more question, Alexei.
Hello, sorry, I'm interested in data. For Marvin, I understand that I can find data at Planetary Plasma Interactions website and have data collaborated and very well structured. Maybe I have delay for 3 or 6 months with this data. But can I find the same data sets for Tiny Wayne 1? Because I see that I can find some data from the papers published, but I didn't understand where can I get the same well-structured all the data from it? Thank you.
Very good questions. For my team, we download the TM1 data from the TM1 data center website. So I think it's possible. You can also download the data from the website, openly, and maybe you can check this paper. We have put the website in the manuscript.
Okay, thank you. One more
Thank
question.
you.
No, I think we have no questions. Thank you again.
Thank you.
So, according to our schedule, we have coffee break now, but we are almost more than 15 minutes in advance. So how can we proceed? Either we can ask the next speaker, who is the first speaker after the coffee break, for the talk now, or we will go for coffee break right now. The next speaker is online, and I don't know if she is ready. Is Jordanka Semkova?
Yes, I'm here.
Are you ready to give your talk right now before the coffee break?
Okay, yes, I can give.
Okay, I think so.
As you prefer.
That we think. I think Jordanka, we should decide right now, and we're thinking.
Okay. Okay.
Right now. Okay. So we can listen to you, and you can share your screen.
Okay, thank you. Let me say that it's my big pleasure to participate in that very interesting symposium, Can you see my presentation?
Yes, yes.
Yes. My talk will be on radiation environment on TGO Mars orbit during solar particle events in 2024. The data used is from the dosimeter Lulin-MO, which is a part of the Friend instrument on TGO. Here we will use data for the particle fluxes, dose rate, and those equivalent rates provided by the Lulin-MO dosimeter in two perpendicular directions. Data must be understood in the context of shielding of Lulin-MO detectors from the surrounding materials, which is very ununiform and varies from 1 to 180 gram on square centimeter, with an average value about 20 gram on square centimeter. For this shielding, the minimum energy of protons, which can penetrate and reach the detectors of the instrument, is 30 MeV. But a noticeable effectiveness of registration of protons starts from energies about 50 MeV. We have data in Mars orbit during the decreasing phase of 24 cycle, its minimum, and during the increasing and close to the maximum of 25th cycle. Here is the data for the particle fluxes and dose rate measured from May 2018 up to now. This is mostly the data for the galactic cosmic rays. The maximum values of galactic cosmic rays, fluxes, and dose rates were measured during March to August 2020 during the minimum of 24 cycle. Since then, they decrease, and in August this year, the fluxes and dose rates of galactic cosmic rays are only about 40% of the maximum values during the minimum of the solar activity. The spikes here, which are superposed on galactic cosmic rays data, are from measurements of solar energetic particle events starting in July 2021. The data for ACP events from 2021 to 2023 were presented during the previous meetings of this symposium and published in papers. And now I'll stop on the data for solar energetic particle events observations in 2024. Here is a list of the observed solar energetic particle events in 2024. The first column represents the start of the event. The next one is the duration of the solar particle event in hours. The third column represents the total dose from galactic cosmic rays and solar energetic particles measured during the entire event, and the dose only from solar energetic particles. Next column represents the maximum values of dose rate measured during this event. And the last one shows the increase of GOES proton fluxes, if any, during these events, and the range of the measured increased protons. The major solar particle event observed until now on TGO started on 20th of May. It lasted more than 64 hours, and here are the values of the total dose and the maximum dose equivalent. This event has a very small influence on GOES, and very small increase of GOES proton fluxes was observed, and this is due to the fact that it was caused by backside flare and CME, but I will talk on this later. Here in purple are shown the merging and overlapping events measured during this time. Many of them are here. Now I'll show any one of the observed events in more details. The first one started on 1st of January 2024, just at 00 hour, like a New Year salute. Here is the data for the particle fluxes in two perpendicular directions measured by Lulin-MO in red and blue are this data, and in red and black, sorry, and in blue are shown the 30 MeV Gauss protons, and in purple are 50 MeV Gauss protons. Here's the mutual location of Mars and Earth, and also Stereo A and SOHO satellites during this event. Mars and Earth are on almost opposite sides of Sun, and during the period until July 2024, they were on opposite sides of the Sun. The sources of this event observed both on PGO and GOES are X-ray flare and hello CME with very high speed. This event was observed also by the neutron detectors of Friend instrument, and also by neutron detectors of Hand instrument on Mars Odyssey. The next event was observed was during February 2 to 6. Here is the data, again, for particle fluxes measured by Lulin-MO and on GOES. And again, the mutual location of planets and satellites. It is seen that on GOES this event has no effect. It was caused by a backside hello CME. A very interesting series of events started on 9 of February and lasted until 15-16 of February. Here is the data for the dose rates on TGO, and on the bottom are shown the GOES fluxes of 10, 50, and 100 MeV during all these events. 3 CMEs are responsible for the increases observed on TGO and on GOES. They are shown here, and another CME, which is associated with X-class flare, caused the increases on GOES on 9 of February, which is not seen on TGO. Here are the sources of all these observed events. These are the sources of the event seen only on GOES. And here are the CMEs responsible for observations both on TGO and GOES. The first one is an East Limb CME. The next one on 10 of February is hello CME, backside hello CME, and the last one is also hello CME. Here is the joint picture of all proton fluxes registered between 6 and 16 of February, both on TGO with red and black, and on GOES with purple and blue. It is seen that some of these events have more severe influence on the radiation environment on GOES than on TGO. And the biggest SEP events observed until now on TGO started on 20th May. Here are the data for the dose rate and particle fluxes during the increasing phase at the maximum and close to the maximum of the events. These are the data for the maximum dose rate and particle fluxes measured on TGO. This event is bigger in comparison with the major SEP event registered in September 1989 on Mir space station at high latitudes and high L shells. It is about 30–40% larger than these previous biggest SEP events. Here are the profiles of the dose rate particle fluxes during this event by Lulin MO, and here are comparison between the measurements of the neutron detectors of Friend and Lulin MO count rates. The total dose from solar energetic particles during this event in silicon is about 55 milligray, which is equal to the dose from galactic cosmic rays received for about 200 days during this cycle of solar activity. The dose equivalent, which is the biologically significant dose, is about 44 millisievert, which is approximately the dose equivalent from galactic cosmic rays for about 57 days. The source of this major event was X12 plus solar flare registered by Solar Orbiter. Here is location of Solar Orbiter over Sun and Mars. It was in good position to observe the backside of Sun, from where the halo CME responsible for increases of solar particles at TGO occurred. This event, as I already said, is practically not observed on GOES. The next solar particle event observed both on TGO and GOES happened during 11 to 14 June. Here is the data for it, and also the CME responsible for these events, which is associated also with X-class flare. Very interesting event started in July. Here is the data for it. On TGO, it consists of two merged and superposed SEP events, and increase on GOES of GOES fluxes is observed only during the first increase on TGO. Even 100 MeV events on GOES increased during these events. The source of the SEP event observed both on TGO and GOES is a massive backside halo CME, which was produced by a very strong X14 class flare. And it was observed again by Solar Orbiter. Here are the view of the halo backside halo smear responsible for observation of SEPs on TGO and GOES. And here is the CME responsible for observations of the second peak in Lulin MO fluxes, which is not seen in GOES data. The next event observed was in September. Here is the data for this event. In September already, Mars and Earth are on the same side of the Sun, but this event are caused also from two backside SCPs. And the last event which we observed was on October 9 to 10. Here is the data for this event. Here the 50 MeV proton fluxes on GOES are by about an order larger than on TGO, and this event caused more significant change of the radiation environment on GOES compared to TGO. It was caused by an X-class flare. In conclusion, the dose rate and particle fluxes of galactic cosmic rays in August 24 are about 40% of the maximum values during the minimum of 24 cycle in March 2020. The dose from SCPs during the most powerful solar particle event on 20th May is equal to the dose from GCR received for about 20 days. 200 days, sorry. The SCP dose equivalent is approximately equal to the dose equivalent from galactic cosmic rays for about 57 days. What is interesting, it is that the total dose from all SCPs during January to September 24 is approximately equal to the dose from galactic cosmic rays for the same period. Some of the SCPs observed in Mars orbit are seen also in GOES proton fluxes. Most of these events are caused by HALO CMEs. The three most powerful solar particle events observed in Mars orbit are produced by far-side flares and associated with them HALO CMEs. All this show that long-term investigations of the radiation conditions at Mars, at least during full solar cycle, are very important for receiving the experimental data for the radiation exposures to future manned missions to Mars, and also for choosing the best time for such a mission. That's all. Thank you for attention.
Thank you so much for a very interesting talk. Questions, please? Yes, Lev Matveyevich.
Congratulations, Professor Semkova. I think Sun is helping you to produce very good and interesting results. I hope it remain active for a long time.
Thank you.
My question, I remember that it was similar measurements, Lulin or Matryoshka, I forget, at the International Space Station. Is it operative now, and could you compare the data? Interesting how these dramatic effects influence the near-Earth space.
Matryoshka experiment is not active more on ISS, and also our measurements in frame of Matryoshka experiment stopped in 2015, but during the operations of Lulin instrument in the frame of Matryoshka project, it registered several SCP events, but they are not so strong like the observed in May this year. They're significantly lower and weaker.
Thank you. One more questions? No? Question? No? From my side, I can say that the sense of this advantage of this talk also has a practical, for example, for users of TGO data, now we can look on these exact dates of event, look on our vertical profiles if we have some impact on these events or not. Thank you.
Yes.
So we have a coffee break now. Thank you again. And we will reconvene. Let's decide. Maybe in 20 minutes it's okay. So not in 4:20, but in 4:25. Is it okay? Since we have one talk less. See you. Dear colleagues, we will continue our next subsession, and the next speaker is Boris Ivanov with his talk New Craters on Mars, Expanding Catalog in 2023-24.
Good afternoon, everybody. I have a very simple talk. It's simply a continuation of my last year talk and many talks many years before, that the perfect spacecraft Mars orbiter make many images every year, and year by year we update catalogs and search for new interesting craters, features. Our company mostly interested in craters, and more detailed discussion about mechanics of cratering on Mars and what we see there, it would be the next talk by my colleague. I tell you some general story of what happened during this year. So to start, I need to remind that we have a set of spacecrafts which very clever imaging system, and we have now a few sets of images of Mars with various resolutions, and the last success, it was Mars Reconnaissance Orbiter with high-rise camera, which can give us images from Mars with a resolution of 25 centimeters per pixel. So even this table would be imaged from the orbit of Mars as 4 pixels, and you can recognize it. And very important that this camera was not the first, but we have a few previous missions with a very good imaging, so we can say something in the past where we have now this modern spacecraft on the orbit, but we can use previous flights to find the same place, say 10 years ago. And as you know, remember last year we very worried because in July 23 it was damage on the camera on Mars orbit, and engineers of the space mission, they finally lost one strip on the image, so we lost some targeting, and somebody was afraid that it was the end of the mission, but now it works, except we have a very narrow gap in images, but we can see by side view. So about this year. This year I mean from the symposium to symposium. The last images of this year, they've been downloaded to the public server October 1st, and the last frame with craters is September 1st. So with the lack of 2 months, we are following the real life on Mars. And this set show you to the left the very old images of 1999 Mars orbital camera, Marin's image. Then we have German Gerhard Neuken cameras, HRSC and ARHC, where we see some feature. And of course with Mars orbiter, with high rise, we see what is this spot on this image. It's a nice crater of 50 meters, one of the largest dated craters. So compare these two images in Mars orbital camera, Marine camera, and HRSC camera. We can say that this crater is, when it was imaged in end of January of this year, it was, we exactly know the age. And after this finding, you can use more data, and you see how this crater was seen in high-res 8 and in CTX in 2010. And comparing this stuff, very often we can say something about surface activity of winds, how quick area are change the color, but this is processing of data which we try to extend. So the progress in the imaging of Mars was permanent, and this is first collection from the paper by Ingrid Dauber and Alfred McEwen in 2009 for the first 2 years of high-rise working, and we see that mostly we see craters in red area on this map, and a red area on this map means it's a very dusty area. It's a dust index which we use thermoscan test imaging can estimate. That's why we never, the team, never pretended to make a global catalog of new craters, but combining 2 cameras with low resolution was wide angle and high resolution was small, very narrow angle, we can work in parallel, finding dark spots. Then we image pointed there high rise, and we can see what I show you. The images. In first 5 years, the map of known craters, it was looking like this one, and year by year we accumulate more and more data, and today is the map of craters where we know craters for which we know at least time interval of formation, so we know the age. This looks like this one. So it's a very long catalog. It's approximately 2,000 craters with various diameters, and we can study crashing rate issue. So we can see how many craters per unit area formed in 1 year and blah blah blah. Then we see that some of craters are not single craters, but a cluster of craters, and we can speculate about destroying projectiles in Martian atmosphere, and we can only be very imaged to see how strong could be Martian atmosphere for the high velocity space projectiles. They cover hundreds of meters with thousands of fragments. And for example, now 2 examples of things which are very, very interesting but we don't have very good theory. What, for example, to the right on the top small image, we can see nice, more or less typical crater, 22 meters in diameter, and we know the date of its origin with accuracy of few months. So it was, we have CTX image without crater, February 23, and high rise. Maybe we have later CTX, not released yet, but anyway, in year and couple of months, we imaged the crater, and we know exactly that this is less than 1 Martian year. And this nice crater, we can speculate about size of projectile for different impact velocities, and the interplay of shock wave, of ballistic shock wave, which is emitted during the flight in the Martian atmosphere, and then explosion, maybe some with water vapors there, spherical explosion, give us hemispherical shock wave, and you see the result interplay of these two shock waves. It's nice what we name scimitar, like bladed squirrel. Another example of the same scimitar, this style scimitars, it's the event of August 23. Crater is very small, 7 meters, but if, and this is just the upper image show how the team works with this vanished strip of color images. We have normal black and white image, we have strip of colored image, and low resolution image cover the gap for high resolution. So this is typical picture where we have a strip. Now most of this stuff is re-imaged. Camera is targeted a bit to the side, so in normal color or only black show you. So to see here the strips, we can use image processing, and to the on the bottom image I show you how this scimitar works. I start was here, go here, then go here, and from this last year I talked about some models about this, but they are not very good, so we continue to work, and the high-rise continue to supply us new and new images. This one especially interesting. You can see how the crater which occurred on the image just inside this non-working strip. The team made a combined strip of low resolution, and we have normal black and white, blue here, colored. So channel works. This is restored map from low resolution images, and finally we can, to the right, we can see general scheme, which is very spectacular. It's roughly a couple of kilometers parabola, or in really hyperbola, and a lot of other footprints of shock wave playing between several impacts. And this is the total deciphering of this stuff is ahead. One of the nice is very young, September 10 of 1022, and here the projectile was shattered in the atmosphere, and about 2,000 fragments created separated craters. Craters excavated darker dust from the below. The territory is covered with light dust, and this interplay gives you scimitar from the largest crater. We believe that is direction of flight, and a few other impacts give us intersection of hemispherical shock waves which go out of the impact, and we can speculate, for example, with accuracy of a couple of microseconds when was this impact occur related to the largest one. It's also in progress. So a couple of words about statistics. Here, repetition of my last year slide, but with additions. So the blue curve, the most of, is what we measured in 70 years of 2007. In 2007, this is the date of estimated date of impact. So for all impacts, we have not enough data in the below 10 meters. When collection of images began to be larger, this maxima going up. So this is roughly half and half. And last 2 years, 22, 23, and this academic year 23, 24, they give us approximately the same number of impacts. For example, in this bin size, 4 to 8 meters in diameter, we roughly imaged 100 of impacts per year. And the next step is to see the nature of terrain, whereas we see how dusty is it, and to outline the territory, which we can say more or less uniform in the sense of probability to find the crater. And this gives us the real impact rate. So it is other interesting thing is to see during the year how when was formed craters which we see now. So blue lines, it's observational period. It's 17 to 19. It's data from the paper by Dauber. And we see that this was the end of the imaging, and during this year the maxima is roughly 5 years behind. Because you have more and more data, and you see then we see next year again this is the end of a real year of observation, and the maximum number of craters you see few years ago. This is an anomaly which I don't know why, but it's very fruitful year 22-23, and this year 23-24 is just the beginning, and now from this analogy we can wait that this curve would be also go up. It help us to take critically the size. And now few things which we should take into account when we discuss this small body. So first of all, we now have not only images but seismic data. This is nice moving how inside put the container with seismograph to the ground. And the paper which was published in June 24, so kind of results. Again, the same team leading by Dauber and McEwen. They compared what we see optically and what we can feel by detecting seismic signals. They published the paper in Science Advance. I'm not agree with all the things, but you can compare at least for small craters. It's the last collection which was published by the team. And this inside seismic data, they are going up. Good question. Is it some shift in logic should be done to join this curve, or we really see only say 1/10, 1/20, each 20th craters which really created on the Martian surface? It means if I shoot here hundreds of times, statistically from this picture, I will see only 30 craters, or 3 craters. And this is the reason to have a very provocative title for this paper. Maybe it's methodology, maybe it was a burst of cratering. And I want to finish just a few days before the meeting, the two papers being published in Nature, both by astronomers and people who study celestial mechanics of small bodies. And what they find? They find that in reality it's possible that only 3 impact events in main belt asteroids produced 78% of all meteorites which we find on Earth. It means 38% of craters which on Mars, I think the share would be the same. They are created by fragments from these 3 events pretty young. Maybe it would be less than 1 billion years ago. And this picture from one of these papers show you the difference between meteoroids 1 meter and observed near Earth objects near 1 kilometer. And this stuff 1 kilometer astronomically observed, we normally use in our estimates to say how many, what is population of different kinds of bodies which bombard us. And what this paper is amazing, they found the way that 1 meter's body would have different percentage in our stuff. For Martian data, which we see, it's very important because we need to have some ideas about strengths of foreign bodies to explain string fields and different, how we go from single impact to pair of craters to the cratering field where you can, the maximum is around 3,000 individual fragments. So this is the results of thinking in this direction for this year, and thank you for the attention.
Thank you. Questions, please, or comments? No? Anna?
I have a question about the test dust distribution.
Louder. Громче.
About the test dust distribution that you show on your crater.
It's not mine.
Yes, it's mine, but it's your finding. It's inside this maximum of dust distribution. Yes, it's.
This is statistics.
Statistics, but it means it's plenty
we
of
have
dust.
A lot of craters outside.
Yeah, it's dust on the surface. It's dust on the surface. On the surface, on the surface. Ah, you don't know. So, because in the atmosphere it's good.
No, this
okay, it's a surface.
It's crater surface.
Okay, it's surface. Okay, thank you.
Some more questions? No? Okay, thank you so much. And we move to the next speaker, Елена Podobная. An expanded catalog of recent meteoroid impact sites on Mars.
My talk is about an expanded catalog of recent meteoroid impact sites on Mars. On Earth, meteoroids of up to 10 meters in size are usually observed during a short flight through atmosphere. In rare cases, their fragments are found as meteorites. Due to more rarefied Martian atmosphere, impacts of such bodies led to the formation of crater fields. Martian surface level corresponds to about 30 kilometers altitude in the Earth atmosphere. So the study of clusters on Mars allows us to study fragmentation detail that cannot be detected in terrestrial conditions and provide a unique opportunity to evaluate the properties of meteoroids independently. Earlier, formation of clusters on Mars was predicted, and then it was discovered. In this work, we are looking at the preceded part of the extended catalog of Martian impact sites. It contains about 40% of single craters and 60% of clusters. Here you can see 3 types of Martian impact sites. It can be a single crater or a cluster, but a pair of craters is a cluster too, but we highlight them in a separate category. And, this is a cluster. To describe clusters, effective diameter is usually used. It is a diameter of a crater which would be formed by an undestroyed meteoroid. We constructed size frequency distribution of single craters and all impact sites. It was fitted by a power fit, which exponent is a good an agreement with independent sources. Single craters and clusters are described by the same distribution. Here you can see size frequency distributions and fits. Most impactors in the expanded catalog are up to 3 meters in size. On Earth, such bodies can be detected by the bolide networks and satellite registration system. Classification and grouping should allow us to identify trends in existing clusters. Earlier, it was suggested to group impact sites into 4 types. Clusters with one major crater and few much smaller ones, one major crater supplemented by numerous small ones, clusters with several comparable craters, and densely populated clusters. On panels you can see size frequency distribution of craters in several clusters. But at the time, only small statistics was available. So we applied this classification to consider data of more than 1,200 of impact sites. And we can see that most part of clusters are concentrated into 2 groups. Other 2 groups contain only 2% of impact sites. So this classification doesn't describe our catalog. We decided to group impact sites by new types, we made a new classification. So we considered size frequency distribution and other dependencies for pairs of craters and for clusters. Single craters were highlighted into a separate group. Pairs of craters can be of 2 types. It can be comparable in size craters, and it can be first major crater supplemented by much smaller second. So we try to highlight pairs with one major and smaller second crater. To determine the boundary of separation, we looked at the ratio between craters. Our catalog contains 90 pairs, and so here you can see the distribution of the ratio of the diameters. And the right panel shows dependency of this ratio on the effective diameter normalized to the main crater. And we suggest to group pairs by the ratio equal to 0.4. It's a moment where an effective diameter become almost equal to the main crater. By the same criteria, we grouped clusters. Here you can see the distribution of 2 largest craters ratio for more than 600 of clusters from our catalog. And you can see that the second group is too large. And as the next step, we look at this group. Here you can see the examples of previous grouping. This is a case when first major crater supplemented by much smaller companions. And On the right panel, there is a case when two biggest craters are comparable. So, as I said earlier, we suggested to select a subgroup from a group with two comparable craters. We suggest to group by the ratio of a third to the main crater. On panels you can see some dependencies for this grouping. Grouping is shown by different color of symbols. And on the left panel you can see a case when three largest craters are comparable, and on the right panel you can see that third crater is much smaller than first. So there is a scheme of proposed classification. Suggested groups are marked by orange frame, and they can be generalized into three types of impact sites. They are first major crater, two comparable largest craters, and three or more comparable largest craters, all supplemented or not by much smaller craters. And for three generalized groups, we constructed size frequency distribution. You can see the different average inclination angle for each of three groups, and we think that different proposed groups may correspond to different destruction type during the meteoroid impact. There is a summary of my presentation, and thank you for your attention.
Thank you. Questions? Yes, please.
Thank you very much. Very interesting. What about craters due to small comets? Is it possible to distinguish sorry, distinguish craters from small comets and meteoroids?
Thank you for your question, and we are working on it just now.
More questions? No? And no online? Oh, thank you again, Helena. And we move to the last oral presentation by Elena Karpovich. She's not, she's here. And online? No? And did he upload your presentation? No. I guess she's absent. And no co-authors. Okay. Her talk is supposed to be in 20 minutes. Okay, but we may switch to the poster session. We have 4 or 5 short talks, 5 minutes talks, but I suggest we can, if it's possible, you can speak not so short, and we can discuss some questions as usual oral talk, because we have quite enough time till 6 o'clock p.m. If you agree, we can switch to the first poster by Nadezhda Chuykova. How can we listen to them? Okay. The next one, Ekaterina Cholovskaya. Ah, yes. You already had your talk. Geological structure of the upper part of Nergal Valleys, Mars.
Hello again. Earlier I spoke about clay minerals in the upper part of Nergal Valleys, and now I want to tell about geological structure. So the main feature of the starting area is the presence of clay minerals, and to identify the relationship between genetically different deposits and their formation process, we had to reconstruct the geological history of starting area. Beside on the identification of stratigraphic units using morphological and morphological analysis, a geological map was compiled. So the two most whispered units characterize the main features of the geological history in the starting area. The first is the Asian highlands with absolute model age 3 and 8 billion years. A characteristic feature of this unit is small channels, which likely mark the first Naihin episode of fluvial erosion in starting area. The second main unit is early Hesperian lava plain with absolute model age 3 and 6 billion years. Hodesher and Nergal valleys were formed within this early Hesperian lava plain. Also, we selected eroded surface around Hodesher and use CSVD measurement to understand the age of formation this surface, and this is 2 and 4, 2 and 8 billion years. So beside on the topographical analysis, we have reconstruct geological history of starting area. So in late Naihin, 3 and 8 billion years ago, late stage of formation of ancient landforms in the study region. After some older fuel channels could have been formed. In early Hesperian, 3 and 6 billion years ago, lava plains was formed. After, in Hesperian time, Hodesher and Nergal valleys were formed. And at the end, in early Amazonian period, there was glacial activity which formed eroded surface around Hodesher valleys.
Thank you. Questions? No questions, no comments. Okay, let's move to the next speaker, it should be Tatiana Morozova, but I was told that there is a withdrawal of her talk. Then another poster is Daria Morozova and Oleg Weisberg. No. And okay, the last one in the list, in this, according to our schedule, is Sergei Kulikov.
Hello?
Okay, he is
Do you hear me?
online. Yes, we can hear you. You can share
Okay.
your screen.
Okay. Oh. Something changing?
Yes, we see your slides.
Okay. Hello, my name is Kulikov Sergey, and today I'll present my poster, Proxies to Interplanetary Conditions at Mars by an Artificial Neural Network. Here is an introduction. First of all, I should start with a brief review of the previous results that led us to use a neural network for solar wind parameter proxy. During the study of the InSight landing platform magnetometer data, we found a moderate correlation between the magnetic field disturbances on the surface of Mars, specifically on the evening side, and the solar wind dynamic pressure. Solar wind data was taken from MAVEN spacecraft instruments. However, approximately 47% of the MAVEN data collected during the InSight operation on the surface doesn't contain the solar wind measurements. That fact significantly decreases statistics. In order to avoid the lack of data, there are lots of methods to proxy solar wind parameters using magnetosheath measurements, and below I will describe one of them. Following ideas described in this article by Ruhunusiri, we developed the artificial neural network. Its architecture is shown in picture 4. It has 20 inputs. In addition to the magnetic field, density, temperature, velocity, and position inside the magnetosheath region, we used the Martian crustal magnetization as an input parameter. Also, the model has two hidden layers with scaled exponential unit activation function on both. The Adam algorithm with Haber loss function was used for neural network optimization. And Haber loss function is commonly used in regression tasks, especially for datasets containing outliers. For training and testing the model, we used the data from the MAVEN spacecraft for the period from 2019 to 2023. In order to determine the intervals when MAVEN was in solar wind or magnetosheath, we used the algorithm described in this article by Halikas, together with the boundary threat-ion model and solar wind ion analyzer data. Resulting parameter distributions demonstrated on picture 7. To bring the data to the same scale, we used two-step normalization. In the first step, we use standard scalar from the scalern library, which normalizes features separately, removing the mean. But the standard scalar is sensitive to the outliers, and in order to overcome these outliers, as well as to scale the data from -1 to 1, a hyperbolic tangent normalization with a variable coefficient was used in the second step. And here are the results. Picture 8 demonstrates predicting prediction results for interplanetary magnetic field, its magnitude and components, as well as for interplanetary magnetic field clock and cone angle for 50 randomly selected cases. Blue dotted line shows the model predictions. As we can see from picture 9, the model demonstrates the greatest uncertainty for the values of solar wind parameters, which are poorly presented in statistics. Same results for temperature and density. For example, the density are accurately predicted until the 7.5 inverse cubic centimeters. The solar wind ion density is less than this value in approximately 90% of cases. And this slide demonstrates the artificial neural network prediction for the solar wind velocity, and here is the table that explains the criteria used to estimate the neural network prediction accuracy. That this criteria was taken from the recently mentioned article of Ruhunusiri. As can be seen, they developed artificial neural network can accurately predict interplanetary magnetic field magnitude, solar wind temperature, velocity, and density, but it has less accuracy in predicting interplanetary magnetic field clock and cone angle. Here is conclusions. Thank you for your attention.
Thank you. Questions, please? No. Yes, one question. Nikita.
Yeah. Hello. One question: is there any kind of method to preliminary estimate how good the artificial neural network predictions could be?
That's a good question. We used criteria which was described in the Ruhunusiri article, but as I understand your question, you mean the limits in general, predictive, or?
Yeah, kind of. I don't know. You could estimate the prediction. You could estimate the precision of the predictions only a posteriori, but not a priori, as far as I understand.
Yes.
And the method to estimate the a priori is a priori is non-existent.
Yeah. Well, and what question is?
No, I'm asking is it exist or not? Okay. Ладно.
I should think about it.
Okay, so some more questions now to this speaker. Thank you again.
Thank you.
And we finish with poster session and switch again to our oral session. The speaker Elena Karpovich, she just came with her talk, Unmanned Aircraft for Mars Exploration, Preparing a Scale Model for Flight Tests. Sounds fantastic. Very nice, with demonstration of real model. So you even have, if you need, more than 20 minutes.
Okay.
Because we have a schedule in advance. You are definitely the last one for today's session.
So colleagues, thank you so much for granting me this opportunity to talk to you here. Being an aircraft designer, to talk to space scientists, so I feel really excited about this opportunity. I believe I'm talking here for the second time. And please let me share with you some recent results related to our Martian aircraft project. So basically we are working on a project of an aircraft designed to fly on Mars and carrying some kind of scientific payload. But let me start by just introducing to our project in general. We are being supported by the Russian Science Foundation, and we are 3 members in a team. We are a team of scientists and engineers. So we have a guy in our team responsible for the space part of this project. I am responsible for the aerodynamic design primarily, but also I manage and organize everything. And also currently I'm involved in building and tuning the flying models, including this one. And if you are interested in it, I can explain you after my talk what is this strange object. Yellow-black color, and how can it fly not only on Mars but on Earth. And I'll be happy to share with you some insights related to this model. We started our project formally. It started in 2022 in April, but actually the history of this concept, please let me show you. This is a box wing concept. Box wing means that the aircraft looks like a box when viewed from the front view, as well as from the top view, just like a box, a flying box. And this layout, this configuration has a series of advantages, especially important for difficult flight conditions, as those we expect for a Martian aircraft to experience in flight. So this concept has been developed at the Moscow Aviation Institute since I was a graduate student there, because, well, probably being a kind of rebellion deeply in my soul, I decided to work on unconventional configuration, on unconventional aircraft, rather than following a standard procedure of, just designing an aircraft using a clear and proven algorithm. So I decided to do something different. And this was this concept of a box wing configuration, basically wing configuration, because, well, it lacks some advantages in terms of aerodynamics and also weight of the structure, which I can explain you in detail, if you like. But basically, by the way, we have a website, so you can go there and read some information related to this project. I try and put there all the relevant and interesting information related to the progress of our developing Martian aircraft. But unfortunately, I believe for 2 months or so, I'm so involved in the work related to manufacturing this thing. Well, it is a small aircraft, but we have a large one as well, because this model is only intended to teach the autopilot to transition from vertical flight mode to horizontal one, because it is a VTOL, a vertical takeoff and landing aircraft. Well, we have a website, and you can go there and see some interesting information, hopefully interesting information about this project. And I was talking about aerodynamic tests related to the box wing configuration. I started being a student at the Moscow Aviation Institute, And I'm extremely happy person and lucky person because I had an opportunity not only to design just a 3 model, this one just create a picture. I also had an opportunity to build my own wind tunnel model, and you can see it here. So on the photograph, lab photograph, with little tufts glued onto the surface of the model. So it is a wind tunnel model, which we tested in our T1 wind tunnel. We have several wind tunnels at the Moscow Aviation Institute. So we tested this model so that we could explore its aerodynamic characteristics in depth. And it is a beautiful story, but my today's talk is not about aerodynamics of this model. By the way, the wing configuration is the same, right? It is a box wing, but it was basically an aircraft to carry human on board. It was intended to be a 2-seater, so a piloted aircraft. And here you can see its wind tunnel model. So it was actually the start of this project, and it happened, I believe, in 2015 or something like that. So when I was completing my graduate studies at the Moscow Aviation Institute. And it is. And after the formal initiation of our Martian project, which happened in 2022 when we won this funding by the Russian Science Foundation, we started by considering all possible technical requirements and limitations associated with the future aircraft. And of course, we thought about how the aircraft might be carried to Mars, our little aircraft, so it must be placed in a kind of descent module, right? Just similar to that, for example, that might be used in ExoMars mission. So we followed a similar procedure. So we put our aircraft as a primary or rather secondary payload into a kind of descent module, which is shown here. And I'm sure you are familiar with such a picture. And after that, it will be injected into the trajectory towards Mars. And also we tried to figure out a procedure for descending in the Martian atmosphere. And again, probably, so there are many letters in the picture, but the idea, the most important part of the picture is at its bottom. Please let me show you to a larger scale. So, one of the most important questions we faced was what kind of configuration to adopt for this airplane, since, as far as I know, still there is no inner field for an aircraft on Mars. And what could we do in this situation? So, the first option is to design a single flight airplane, right? Just a conventional wing tail. So we have a little representation of a wing tail configuration here, just a conventional normal airplane. But unfortunately, it would be rather fated to complete just a single flight, right, with no possibility to take off under the single landing. So the opposite option, or rather alternative option, is to design a VTOL, vertical takeoff and landing aircraft. And here we have, again, a little representation of this concept of a vertical takeoff and landing aircraft capable of taking off from the stationary platform, resting on the surface of Mars, and just fulfilling its function and operating on Mars for probably, hopefully, 3 years or something like that. And here you can see the very first options for the airplane configuration we considered. The blue one is the solar airplane, a conventional, so wing tail airplane, a single flight one. And the green airplane, is a rocket engine. So we conducted lots of calculations in order to figure out how long might be its endurance, how little small might be its size, and well, what might be the maximum volume of its fuel tank. So the most conservative calculations showed that probably the expected endurance of a rocket engine, the wingtail aircraft, might be of about 12 minutes or something like that. And take into account that these two aircraft, they are quite large in size, so they are intended to be the primary payload. So in summary, we decided that it is not that interesting, would not be too much interesting for scientists to use a single flight large aircraft flying for only 12 minutes on Mars. And here is why we decided to switch to this box wing configuration. And actually, I'm not sure if it was fate, just because I spent so much years working on this concept, but we decided that this option is the most promising in terms of efficient aerodynamic size and structural weight. And here you can see different stages of the work on this concept. So we started with the pure aerodynamic analysis and tests, right, using our wind tunnel model. But now actually we are ready for flight tests. And in the middle of the slide, you can see, well, actually this model, the brother rather of this model, ready for flight. And at the end of this PPT, I even have a video showing how this model is performing the most difficult part of its mission, that is landing with crosswind. Because just imagine such an aircraft landing in this position with a crosswind from side. It will like a turn because the center of gravity, so the heaviest part of this aircraft is the battery. It is not attached to it right now, but it is located here. It is quite heavy in comparison to the airframe. So we believe that, well, this model can be unstable during vertical landing, of course, takeoff as well, under the condition of strong crosswind. But again, I have a video showing how it is possible to do if the model is designed correctly. Okay, and also we considered how we might fit all our configurations into this descent module, just because, well, the size and the shape of the descent module is just one of the most important limitations imposed on the aircraft, right? And in the three cases, you can see here, the model is large. But as I told you, probably it is more realistic to consider this model to be a kind of secondary payload, right? So here you can see our little aircraft, slightly larger than this model. Its span is about 1 meter, lying at the side of a larger object, which might be, for example, a rover or a stationary platform. Well, something big, right? And here we have some place for this aircraft, just like, Ingenuity helicopter was delivered to Mars as a secondary or primary third-order payload, right? The same situation. And we invested a lot of time and effort into making sure that we can fit all the systems and equipment required for the model to operate on Mars inside it. So here you can see on the pictures, but of course we have done lots of calculations in order to be sure that the project is feasible on the conceptual stage, of course, conceptual level. And now let me share with you some of the specifications related to the Martian, not the Earth's one, but the Martian version of the aircraft, because this one was designed to fly on Earth only. So I start with the mission, with the function of the airplane. And here we are still considering two basic options. Either the aircraft is going to investigate the very bottom part of the Martian planetary boundary layer, because it can, the calculations show that the small version of the aircraft is capable of elevating only about 190 meters above the surface of the planet, while the thickness of the boundary layer, of the planetary boundary layer on Mars is much, much larger, especially during daytime. As far as I know, it is about 3 kilometers, maybe, maybe about 3 kilometers during the daytime. So the first option is to investigate the parameters of the atmosphere. And here the airplane can either carry a kind of a set of instruments from point to point, from place to place on the surface, or to carry some studies during the flight time, in flight. Another option is to try and investigate in the hovering mode, in the vertical flight mode, some inclined walls like those of craters and canyons. And we believe that this target is currently not achievable by other probes existing on Mars. And again, the depth which can be investigated by this type of probe is only about 150 meters below the surface of the planet. Still, hopefully, this aircraft is would be capable of bringing some value to scientists on Earth by doing that. So the two options, planetary boundary layer and also the walls of craters and canyons. And at the very beginning of our work on this project, we have discussed with your colleagues two suites of instruments to put on board the aircraft, but at that time we expected the aircraft to be larger, so the payload, which is shown here, the mass of the payload, which is 5.5 kilograms, is slightly less than the current takeoff mass of the airplane. In any case, we considered what exactly instruments can be carried on board the airplane. And here I have some estimations of the flight performance of the airplane fulfilling various missions. The most simple one, just carrying the payload from point A to point B, and here we can estimate, you can see the expected range of the aircraft, which can be up to 73, but taking into account the accuracy of analysis at this conceptual design stage, well, it can be about 70 kilometers or something like that. And by the way, the speed of the airplane is going to be quite high for such a small vehicle compared to those on Earth, just because of the fact that it is so hard to fly on Mars. So in order to produce enough lift for the airplane, for the lift to balance the weight, the speed of the aircraft is going to be quite high. In this case, about 48 meters per second, with a minimum speed of about 45 meters per second or something like that. Another option we considered is just the mapping of the surface. And here we, as input data, we used the specifications of a standard commercial LiDAR. And it seems that, well, an average area which might be mapped by this airplane during one flight is about 1 kilometer squared, but the density of points in the resultant data is going to be quite low because of the high speed of the airplane. And the third option is investigation of different things in hovering mode, either elevating or descending into the depth of a crater. And we can expect here the vertical speed of about 1 meter per second, and as I told you, maximum altitude or depth of about 190 meters. And now let's talk a bit about, well, the topic of my talk today, which is about flight tests and preparation for flight tests of such an aircraft. Since the conditions expected for the Martian version of the airplane are so different from those experienced by aircraft on Earth, we must ensure that different types of behavior and also the physical phenomena experienced by the aircraft on Earth resemble, just to a certain degree, those experienced by the Martian airplane, in the future. So there are many approaches to do that, but the truth is that it is impossible to fully replicate all those behaviors and all those phenomena on Earth, unfortunately. And actually, even when we just create a scaled model of a large airplane intended for flying in the stratosphere on Earth, we cannot model entirely the same conditions in our wind tunnels. It is just impossible, unfortunately, but we have various tools to tackle this problem. And the primary approach is to test different models under different conditions. So we slice the problem into chunks and solve it separately. The same thing about our flying model. And we decided to start with the basic aerodynamics. So our intention in the first stage of flight tests was to try and replicate primarily the so-called Reynolds number, that is the effect of the viscosity of the air or the atmosphere on the aerodynamic behavior of our aircraft. And also there is a secondary purpose we believe to be important for us, that is to demonstrate something, right? To demonstrate that such a model can fly and fly efficiently. And we have various tools to estimate that efficiency, the aerodynamic efficiency. So my slide says that there are aerodynamic, dynamic, aeroelastic, and also demonstrative scaling. And in the first stage of our flight test work, we are focusing on aerodynamic scaling primarily. And I mentioned this Reynolds number. Physically, it just shows the ratio between inertia and viscous forces in the air. It shows how much viscosity affects the aerodynamic behavior of an airplane. The higher is the Reynolds number, the greater is the role of inertia forces, and the smaller is the role of viscosity, the better airplane flies. The Reynolds numbers expected for Martian conditions are extremely low, typical for, just small aircraft just like this one, flying at a very, very low altitude on Earth. And not only just in general on low altitude, but also primarily in cities, in urban terrain, where the turbulence intensity is high. So on Mars, the turbulence intensity is extremely high, as far as I know, and it may approach 20%. And this number, 20%, is characteristic for, compressors and very heavy loaded internal tubes and something like that, so compressors, something like that. And the maximum expected turbulence intensity in a city may be of about 15%. And actually, I'm not aware of any wind tunnel experiments where the turbulence intensity greater than 7% was actually modeled. So we even do not have experimental data related to the effects of high turbulence on aerodynamic characteristics of airfoils and aircraft. In any case, we have some tools just to try and model this condition. And I would like to tell you a couple words about the role of demonstrative scaling in our work. Why I'm mentioning why one of our goals is to try and perform a kind of demonstrative scaling. Here on this slide, in the graph, you can see in the middle of the graph this downward inclination of the curve. This graph basically shows how the amount of resources is changing throughout the available resources from different sources, So how this amount can vary with time throughout the life cycle of a complex system. And this graph resembles the world's experience in our technological area. So the graph shows that typically basic research and sometimes applied research are typically funded sufficiently so that all the required experimental and theoretical investigations can be conducted, being supported by those funds. And also, from the moment large businesses and also private companies began to be interested in the system, they also start to fund those systems. But there is a short period in between, called here technology development, the period when the interest from the side of government, since it is not a scientific endeavor anymore, lacks. And at the same time, it is too early for the private companies to get interested in the project. So what can be done in order to survive this so-called valley of death? And I feel that we are approaching this valley of death. So probably we can try and investigate as more time and effort and resources we currently have to make sure we are capable of tuning and improving and refining our concept, as well as the physical objects we are creating. And also, from our side, we are trying to do our best to find alternative applications for this concept, because we really believe that it is feasible, not only for Mars. Well, if it is feasible for Mars, it must be feasible for the most difficult conditions on Earth. For example, currently we are considering this model to be a nice prototype for a meteor drone, for an aircraft carrying various meteorological tools and instruments. And actually we had a couple of conversations with the scientists from the, how do we call it, Institute of the Physics of the Atmosphere or something like that, who actually developed various tools for measuring atmospheric parameters. And they agree that there is some sense in trying and creating a flying vehicle, an aircraft of such a shape, being so compact and aerodynamically efficient to carry meteorological instruments and obtaining information on weather and atmospheric parameters in order to provide airports and other services with the relevant data. And also, I have a slide explaining one very interesting concept. Actually, probably you suppose that the shape of this aircraft, it is just an arbitrary shape because this aircraft is intended to help us test our autopilot. But the shape of a larger airplane, just give me a second, I will show you a larger airplane. So, I see that I don't have just a second. I believe I forgot to put here just a large photo of the large aircraft. And here you can see only the 3D model of a larger aircraft. So it is already built, this aircraft. And, this is the model of a Martian airplane scaled for the tests on Earth. And the shape of this airplane is different from that of the Martian one. Just because in order to replicate the aerodynamic phenomena expected on the airframe, we do not need to create just the same, geometrically similar model. Actually, in fact, the opposite should be done. We must design the shape and in particular the airfoils. Just let me show you. The airfoil, so it is a cross-section of the wing of a model. So we have a tool, a software, which helps us to optimize, to obtain a shape of the wing which would produce the same aerodynamic phenomena under different conditions, so that we can be sure that the aerodynamic behavior expected on Mars can be replicated here on a low altitude of about 5 or even 1 meter above the ground here on Earth. So our approach to scaling is to design the shape for the airplane which would produce the same aerodynamic effects as those on Mars. And we have a numerical tool to do that. We have a program created in MATLAB which can do that for us. And it is one of the most powerful output of the entire project, the thing which I am extremely proud of, together with another tool, which is the tool intended to design a propeller. There are 6 propellers. I don't have any here, but you can see here 6 motors. Actually, this model is fully ready for flight, except for one thing. We must teach its brain to transition from vertical to horizontal flight mode and vice versa. So 6 propellers, and a special thing of this model is that, there are many of them actually. There is no fuselage. Sometimes they ask me, where is the fuselage? It is not an aircraft. We don't need, actually here we need this thing to attach the battery. In the Martian version of the aircraft, being a larger one, we do not need any. And actually, for the larger model, we also do not need any additional. Where is it? Sorry, just a second. I will show you to prove that there is no fuselage on this model. Because the batteries, they are green objects in the middle of each wing. The batteries being the largest objects on the entire airframe, they fit inside the wing. There are 2 batteries and 6 propellers. So we need 6 propellers because the propellers are used, to propel the model, to make it move through the air, and also to control the model. So the model is controlled throughout the flight, just like a quadcopter, by using differential thrust. There is no control surfaces, as you can see here. And control surfaces are a great source of drag and also complexity and weight, right? So if there are additional surfaces, the weight of the structure will be much heavier, right? And by the way, this little guy, or girl, I don't know, this little guy was printed out at my home just a couple of weeks ago. So I have a 3D printer, and actually I have had it for a month, I believe, and now I can't imagine my life without it. Yeah, and I believe it is quite funny. Sorry? No, it is the first time it appears before an audience. So, probably I'm talking too much. Thank you so much for your attention. The last thing I would like to tell you is that we believe that there is some future to this model. Formally, our project is going to be completed in December of this year, but for sure, the model, the large one we are building right now, is not the last one, because we are thinking about high altitude tests. So we will do everything possible in order to ensure a long and successful life for this project. And well, hopefully I didn't overload you with the information. Thank you so much for your attention and your time. And if you ask your questions, I will be happy to address them. Не знаю, если хотят, я могу показать, да.
Thank you so much.
You're welcome.
Questions, please. Yes, we have 10 minutes for discussions and questions.
You have propellers like in a copter and so on. Are you planning to compute the magnitude of the shock wave, not magnitude, but impact of the shock wave on the sample? For Mars is your sample, and to lift off, you need to start the copter, and there would be an acoustic shock wave down the surface. When you will land down, it would be acoustic shock wave again, and so on.
Mm-hmm.
Are you trying to kind of modernize this?
Thank you so much for this question. In aerodynamics, we aircraft engineers by shock waves understand the waves related to the speed of sound occurring somewhere on the airframe, right? Are you talking about shock waves related to
shock waves which propellers will produce on the surroundings?
The noise, you mean, right?
Yeah, noise.
No. I see. I see. Thank you. No, this kind of investigation we have not yet done, but everything related to the operation of propellers themselves, we sure constitute in our project.
Okay, Daria?
Yeah, I have like another question about the construction, about the model. It looks like because you have 4 propellers, it's a bit busy, like already loaded with some elements. But where you expect to put any payload if possible, or it's just where on this surfaces of the model it can be put?
The payload, well, this is the Earth version of the airplane, and everything. We have lots of payload here inside. Actually, lots of electronic components. They all fit inside two how do we call them? 2 compartments inside the middle of the wing here. If you see my arrow, or how can I show you? In the middle, so where you can see the green sports battery, so there are a huge amount of space inside. And all the people. Huh? No, this model is a different one because it is a small aircraft. So the structure is different because it is just a plastic printed out on a printer. while, believe me, I spent a month, just full-time job, a month, building this model from foam, plywood, plastic, just like this one, but there is a small amount of plastic parts in that version of the model. Foam, plywood, and also everything is connected by those black, well, we are grayish, gray carbon tubes. So the structure of this model is extremely different from this one. This can be printed just automatically within a week if I don't want the printer to work during nights because it is noisy. If I can, if I allow it work during night, it can do the job within 2 or 3 days, I believe. So the structure is extremely different. And also actually the shape, because there is no anything like that in that model. So in terms of aerodynamic behavior, the larger aircraft is much more efficient. If we compare the structural weight ratio, so the ratio between the weight of the structure and the take-off weight of this aircraft to that aircraft and also to the Martian one, the difference will be just dramatic because it is a heavy aircraft. For an aircraft, it is heavy because it is made of plastic, which is not. There is no. For this aircraft, we don't want anything from this aircraft except for help us on that aircraft. This is the Earth version. So for the Earth version, we have lots of sensors like. How do we call them? So the sensors are capable of measuring local temperature, for example, to investigate the boundary layer. How do we call them? So temperature sensors, just like hot wire, something like that.
You can
and
just
also.
Excuse me, maybe you will discuss it during welcome party, these details.
Okay.
You told that you also have some video, yes?
Yeah.
How many minutes, how long is it?
I believe 30 seconds or something like that.
Okay, it is short. Okay, because we have 5 minutes before
Well, but it is
finish.
not necessarily.
Okay. So
Only if you want
maybe someone else has some question. I have one question, one general question actually. So you know, comparing with Ingenuity helicopter, American helicopter, which is operating now.
No. It has been broken in
Okay,
December or something like
okay, broken, but it was operating for 3 years. From time to time. Comparing with this helicopter, what is advantage of your instrument on Mars?
Yeah.
Of your aircraft?
Yeah, just give me a second. Actually, I have a separate slide comparing. Comparing. Or probably I have deleted it. Sorry, I believe I deleted. Well, addressing your question, what is the advantage of an aircraft compared to a helicopter, right?
Yes.
So, an aircraft can carry a greater load and also fly a longer distance with the same weight, just because an aircraft can produce lift, balancing the weight in horizontal mode. But sure, our aircraft has to be a vertical takeoff and landing airplane. For this reason, the power plant, so the engines, the motors, propellers, and also the electrical system supporting propellers and motors, so they are going to be much heavier than they would be for just a conventional airplane. Still, the range of the airplane can be much longer than for a helicopter. And unfortunately, I believe in this slide comparing the ranges and the time flight, and also the required power and thrust, available thrust for our airplane and Ingenuity. I'm sorry for that, but well, the short answer is longer range and heavier payload.
Okay, thank you.
You're welcome.
And also, maybe one comment also. We are about Mars now, but if you consider to design such an aircraft for Venus clouds, it would be good because flying inside Venus clouds, we can resolve many scientific problems.
Actually, I believe I've seen a paper on this topic. I believe I have some colleagues at the Moscow Mission Institute working on such a project.
Mm-hmm.
And I don't know why actually there are much more projects related to airships on Venus rather than airplanes.
Airships?
Airships.
Oh, okay.
Because actually Soviet Union has launched a couple of them.
You mean balloon?
Yeah.
Yes, yes. And here in our exhibition, in our museum, we have one huge balloon. Yes.
Yeah, and I wonder why there are many projects related to airships rather than aircraft.
Maybe it is because more easy to design. I don't know. Yes, this is a video. Yes.
Yeah. Here you can see not this model, but a kind of brother of this model. One of our colleagues currently lives in Florida, and he already tried to build such a boxing airplane and make it fly. And he is currently in the process of tuning the controller, just like we are doing. So we use his experience in tuning and setting up electronic components for such a complex set of flight modes for an airplane. And here you can see this small white boxing aircraft landing in crosswinds. So this is not the airplane flying here in Moscow. This is the airplane designed by my colleague, designed, built, and operated by one of my colleagues. And by the way, the same person is responsible for the structural design of our large aircraft. So it is just an invaluable contribution to the project. And if I have some time, we have another video in the same PPT.
No time.
No. Because the flight, the wind tunnel test. But okay. So unfortunately, I cannot show you the video from our T1 wind tunnel.
Or maybe next time, or on some seminar.
Okay.
Yes. Workshop. Thank you again so
welcome.
much.
You're welcome.
And thank you for your brilliant English. Actually,
thank you
yes,
so much.
really impressive.
I work hard every day on my English.
Okay, now let's maybe introduce to all of participants of this Martian section. We finish now, and then in few minutes we should have some welcome party, but I don't understand where exactly. In exhibition or here, because some people told me that it will be here, but here you see no bottles, nothing. We should wait. I don't know. Or maybe at coffee break side. I don't know. Олег, вы знаете где? Надо Оксане звонить, потому что. And one more announcement. I guess in 1 hour at 7 o'clock, one movie should be here concerning Lake Vostok. Yes, with comments of our expert, astrobiology expert Oleg Katsubenko. Здесь? Где все? Okay. So it should be here. Welcome party should be here. We should wait.